This channel does not promote or encourage any illegal activities. All contents provided by this channel is meant for educational purpose only.
Hello, my name is Keith Barker, and on behalf of the entire CBT Nuggets family, I'd like to welcome you to this course on IPV4 Subnetting. Let's begin. Let's start off by verifying that you and I are in exactly the right place at the right time by answering this question together. Who was this course created for? And in a word, it was created for you. For example, if you are working with any of these vendors right here, Cisco, Juniper, HP, Palo Alto, Checkpoint, or any other major player with networking gear, it is very likely that you're going to be working and dealing with IP addresses and subnets all of the time. A big challenge for people who are just coming into the world of networking and certification is that they get beat up, I mean big time beat up by subnetting in those entry-level exams. Maybe up to 30 or 40% of an exam is surrounding IP addressing and subnetting of some type. So if you are a certification candidate, especially for the entry-level certification candidates, you absolutely want to make sure you take this course. If you're a network penetration tester, it's very important to understand subnets. For example, if you're a pen tester and you're doing an authorized scan of network devices, you may want to be familiar with how to calculate subnet ranges so you're setting your penetration testing on the right sections or summarizations of networks. And what I find a lot is there's end users who just want to know more about how IP addresses work in general. This is a perfect opportunity for you also to get that better understanding. And then one of my favorites that's near and dear to my heart is a manager who just wants to better understand what his technicians are talking about. So when the technician is talking about a /28 or a /25, the manager can have a really good understanding of what that technician is saying just by participating in this course. I also am going to add another one down here, and I'm going to put a line there. I'm going to let you fill in that one. There could be server administrators who are working with operating systems, which are connected to networks, which are usually subnets. That would apply. And we could probably make several more. I'm going to ask you to go ahead and in your mind, fill in that last blank. Who also would benefit? And out of all of these items, it's very, very likely that you, my friend, are the prime candidate for this course. And I am super excited to share the time with you. Let me give you a brief tour of what we're going to cover together in this course. We're going to start off with the basics of IPv4, the classes, the default masks, private IP addresses, taking a look at binary because after all is said and done, and I'm going to share with you a boatload of shortcuts that you can use, we still absolutely deserve to understand what's really happening in binary behind the scenes, including the ability to convert on demand between decimal and binary and back. The importance of the mask, how we're stealing host bits to carve out custom subnets, identifying those subnets, identifying valid host ranges on each of those subnets, making sure that you and I have enough host addressing space available on our new subnets for all the computers that need to be there, how to reverse engineer the process. For example, if we're given an IP address with a mask, how do we take that and then reverse engineer to determine very quickly what the actual subnet is that that customer is connected to? The process of summarization is also huge and very, very important. For example, with network statements or creating summary routes, we're going to be using the techniques of summarization. So we're going to cover that in this course as well. And in a Cisco environment, wildcard masks are also an important aspect of working with summarized or custom subnets because they're needed inside of access lists and network statements if we're going to configure a Cisco iOS router correctly for custom subnetting. In non-octet boundaries, we'll take a look at how to start our custom subnetting somewhere in the middle, not on a clean octet boundary, and that's a really important precursor to doing the job of variable length subnet masking, where together we'll walk through soup to dessert, the actual carving out of a variable length subnet masking plan, and at the end of that video, if you follow all these with me, you'll be able to do the exact same process. And the cool thing is, as we go through these videos together, you'll be gaining these skills and improving your knowledge so that by the time we get to this last video called the final exam, you'll have not only the knowledge of how to do something, you'll also have the measurable skills to do it. And that translates to taking those really awesome subnetting skills that you're going to gain and applying those to your networks that you deal with and manage on a daily basis. And that's what gets me so excited about this course, is because it's going to make a difference in your life as you work with IP subnets. Now, I realize that we all come from different backgrounds and we're at different levels. So here's what I did for this course to optimize your time. I'd like you to take all these videos in order. So video 1, 2, 3, 4, 5, all the way up to the very end. But here's the challenge. I know that some of you have some already pretty great subnetting skills. So if you're going through video 1 or 2, you may already have all the knowledge from that specific video. So here's what I did. In every single video, I've got an opt-out section at the beginning. And here's how they work. At the beginning of each video, there's these opt-out questions, and you simply read through them. And if you know the correct answers to those questions, you can safely and comfortably skip that video. So for example, if we take the opt-out for video 2 and video 3, we look at video 4 and we were looking at the questions, we don't know the answers to them, we can then jump in right there and then continue our journey all the way to the end of the course. This is also very handy if you want to go back and review this course at some future time. By starting the video, looking at the opt-out questions, you can very quickly assess whether or not you need to revisit the content in that video, or you can just go ahead and answer those questions and move forward. So we're taking absolute care to optimize your time in this course. Another question that I'd like you to ask yourself is, how good do you want to be with IPv4 subnetting? Perhaps you just want a casual understanding so you can jump in the series, and then once we get up to variable length subnet masking and some advanced topics, you can go ahead and say, you know what, that's enough for me. I've had enough. But if you are the type of person which wants to be in like the top 10% of people who understand how IPv4 subnetting works, I would strongly encourage you to take this course all the way from the beginning, go all the way to the end, and then review those pieces where you want to make sure you have those skills mastered. Now, to that end, also in every single video, I've embedded some expert exercises that I want you to do along with me. And as you participate with me in this course, that process of watch, learn, and conquer will become a reality as you master the skills of IPv4 subnetting. One of the reasons I'm so passionate and excited about this IPv4 subnetting course is because this is the course I wish someone had created for me about 2 decades ago when I was first learning about IP version 4. So the great news is that this course is available to you, and I'm so excited about sharing this knowledge with you. Your action item right now is 2 basic things. Number 1, I'd like you to grab a paper and something to write with, and then I'd like you to click next to start the very next video as we begin with our basics of IP version 4. I am so excited about beginning this journey with you right now. I hope this has been informative for you, and I'd like to thank you for viewing. Putting the fun into IPv4 fundamentals. Let's begin. If you, like me, find that time is very, very valuable, I want to make sure I optimize both of our time together. What I'd like you to do is I'd like you to pause the video and read through each of these 4 questions. If you can correctly answer and are comfortable with each of these questions, go ahead and skip this specific video, and I'll see you in the next video in this course. If, on the other hand, you find that you're not quite yet comfortable with one or more of these questions, have no fear, because you and I are going to address each one of these in this video. I'd like you to visualize in your mind's eye the home where you currently live. Whether it's an apartment, maybe it's a condo or a house, I'd like you to visualize what the roof looks like, what the front door looks like, and also I'd like you to look at, in your mind's eye, the address on your house. So I'm going to draw this house, and let's say the address, just for our example, is 123. Now I know that house number that you have might be slightly different, but one common thing that all homes have is they have an address. And not only do they have a house address, they also have a street address. For example, your neighbor over here at 125 and your neighbor over here at 121. They all have house addresses and they are all connected to the same common street. So let's say this is Elm Street, and I've got a question for you. Why is it that we use street names and house addresses as part of an address? In fact, why do we have addresses at all? And you might be saying, well, Keith, you have to have an address. For example, let's say that the mail carrier wanted to deliver mail to this house. If the mail carrier didn't have any idea about streets and house numbers, these addresses, if you will, we wouldn't have the ability to deliver or even get to a specific location. And that, my friend, is absolutely true. Addresses are very, very handy in the real world that we live in for both knowing where places are as well as the ability to deliver something like a piece of mail to that destination. Well, in computer networks, we also have devices, and we call them lots of things on networks. We could call them, for example, a host, or a node, or a server, or a PC, or a network printer, but they're all devices that sit on networks. And they also have host identifiers, similar to a house number. For example, this may be 121, this may be device 123, maybe this is device 125. And because they are all connected, in this example, to the same network, maybe this network is First Street. Now, in computer networks, we don't actually call it streets. We call them networks. So I could actually say, instead of First Street, we could call this network number 1. So this device right here could be addressed, if you will, from a logical IPv4 addressing system as being host number 121 on network number 1. Just like this house is house number 121 on Elm Street. And what's the benefit of that? Now, the cool thing is that if we ever need to deliver packets, for example, to 121, this host at this host address on this network, because we have this logical IP addressing, which is very similar to street names and house numbers, we now have a method of identifying an individual host, an individual device on that network, so we can forward data called packets to that destination. So in answer to these first two questions, what exactly is an IP address? It's a logical addressing system that identifies networks that are common to devices and individual host addresses for each of those devices on that network. And why do we use them? The answer is simple. It is for the exact purpose of being able to send data to a specific device on a network, based on a layer 3 IP address. Let's chat about what an IPv4 address would look like if we were to see one. Now, in the example of our house and the street names, we had house number 121, Elm Street. That's pretty straightforward because we're used to it. With IPv4 addresses, instead of using names for the streets, we actually use numbers. And it would go something like this: 11.23.14.95. And these periods here are the just separators between the numbers. So an IPv4 address is 4 numbers, 4 decimal numbers separated by periods. And a lot of times people say, well, what's up with the periods? Why are they important? Well, if we didn't use the periods and we just had an IP address of like 11.23.14.95, that might be misinterpreted to mean, oh, it's 112 for the first number, 3 for the next number, 149 for the third number, and 5 for the last number. So the periods here are simply visual and representative separators between the 4 decimal numbers. So here's our first number, second number, third number, and fourth number. And the periods are separating them. So whenever we hear the term dotted decimal, all we're talking about is a format where we have 4 individual numbers separated by periods. Now, one of the cool things is that everybody who's connected to a network is going to have an IP address of some type. The biggest IP version out there at the moment is IPv4, and that's what this series and this course is all about. There's also IPv6, which has been making inroads for many years, and if you want to learn more on that, go check out my IPv6 series dedicated to that subject at CBT Nuggets. IPv4 is still going strong and is still the most popular IP version being used on the planet today. So how exactly do we find our IPv4 address? And the answer is really simple. If you're on any version of Windows, you'd simply run the command ipconfig, just like that, and it's going to reveal to you your IP address. If you're on a Macintosh, you can use ifconfig, and that will show you your IP address. If you're on a Linux box, you can also do ifconfig, and that will show you your IP address. And if you're on some type of a PDA, in the settings, it'll also be able to show you what the current IP address is on your device. And for most of the computers that are connected to IP networks, that IP address assignment of how you actually got that IP address to use is done dynamically through a protocol called Dynamic Host Configuration Protocol, so that you don't have to manually plug in an IPv4 address. You are automatically assigned one. So here's what I'd like you to do. Whether you're on a Macintosh or Linux or any flavor of Windows, I'd like you to right now identify what the IP address is that is running on your computer. So again, if you're on Windows, you can do an IP config like I'm doing right here in this demonstration. And what this is showing me is that my IP version 4 address is 192, that's the first number, 168, that's the second number, 1, that's the third number, 15. And the little periods are simply separators between the numbers, so we know where one number starts and the other number stops. And if you're on Macintosh or on Linux, you'd run ifconfig to get similar results regarding what your IP address currently is on your device. So here's what I want you to do. If you haven't already, go ahead and pause me and then run ipconfig or ifconfig on those other platforms just to validate what your IP version 4 address is, and I would like you to write that down on some type of paper. Once you've jotted that down, go ahead and give yourself a pat on the back. Great job. Because, my friend, it's small incremental steps that are going to give you the skills, the expert skills that you need as you master not just IP version 4, but also IP version 4 custom subnetting. The next thing that you and I absolutely deserve to chat about is dividing lines. What do you mean, Keith, dividing lines? Well, you know, in a house and street, there's the actual house number, like 123, and then there's a space, and then you have like Elm Street. So the mail carrier knows exactly what the house number is versus the actual street. Well, in an IP address like this one, we'll use mine as an example. In this address, which appears as 4 numbers separated by 3 periods, that's the dotted decimal format, the reality is that a portion of this IP address is representing the actual street or network. And unlike like Elm Street with house addresses, we put the actual network portion first, and then we have a dividing line, and then we have the actual host portion. So this would be like the street, and this would be like the house number. So if this is your first exposure to how IP version 4 addresses work, you just got to get used to the idea that they're going to put the street name first, which is just a number, and then the house number after. Now here's the big question. We have 2 parts. We have a network portion and a host portion, and a dividing line. The question is, where is that dividing line? For example, is it between the 192 and 168? Is this all network and this is all host? Or is it in the middle between the first and second grouping? So is this all network and is this all host? Or is it right here between the third and fourth octet, which would make this all the network address and this is the host? For example, if this was the case, where that's where the dividing line was, we could say that the network is 192.168.1, and the actual host, or house address, if you will, is 15 on network 192.168.1. So that's the 2 distinct and separate portions of an IP version 4 address, is that there's a network portion, which is always going to be somewhere on the left, and there's going to be a host portion, which is always going to be somewhere on the right. Where one stops, the other begins. And now for the $1 million question, what is it that identifies where that dividing line is? And the answer is, it is the mask. For example, if we took that same IP address of 192.168.1.15, and I'm going to put the mask in green. If we put a mask like this and said, these first 3 numbers, which are also referred to as octets, and we'll get into more of the binary in a separate discussion, but these first 3 numbers, or first 3 octets, if the mask is indicating that those are all network, meaning they are representing the network, what is implied, which is not explicit, but it's implied, it's implying that the last number, or the last octet here, is available for host bits. So I want you to think of it like hungry, hungry hippos. Whatever the mask devours, for example, in this case, the mask devoured the first, second, and third numbers. And because the mask didn't use or chomp up, if you will, or take the last number is available for host addressing or house numbers on our IP networks. So here's the deal. We are going to get into the details and the math a little bit of behind why that works. But for this video, I want you to understand that the mask's only function, the only function of the mask, is to identify where the dividing line is between the network, which is always on the left somewhere, and the host address, which is going to be on the right. Hey, let's do another example just to reinforce that. Let's say we have an address of 10.20.42.99. Now my question for you is, okay, where is the dividing line for this IP version 4 address? Is it between the 10 and the 20, or the 20 and 42, or the 42 and 99? What you should be saying, and what I want you to say is, Keith, I don't know because I don't know what the mask is. For any IP address, it's the mask's responsibility to explicitly say this portion of the IP address is the network. So for example, if I told you that the mask was like this, and now if I asked you, okay, which portion of this IP address represents the actual network address, you'd say, Keith, that's easy. That's the job of the mask. The mask indicated that the first two numbers are exactly the actual network address. And that implies that the last two numbers, which were not consumed by the greedy mask, are available as house addresses, or in the case of an IP version 4 network, host addresses. So the little computer that's sitting on the 10.20 network could have the host address of 42.99, and what we'd actually see on that computer itself would be an IP address that looks like this, 10.20.42.99. It's all put together in one consistent string, and it's up to the mask to identify where that dividing line is between the network portion and the host portion. I have had a blast. Here's the action items I'd love for you to do. I'd like you to revisit those opt-out questions at the beginning of this video to make sure that you are now comfortable with each and every one of those. Secondly, any of the exercises that I've had you do in this video, for example, in this one we did a look at our IP address with ipconfig or ifconfig. If you haven't done that yet, please take a moment and make sure you do these small exercises. Inch by inch, life's a cinch. But big changes are often very difficult. My objective for you in this course is to make it very simple, and if you'll follow along with me step by step, we'll have you doing custom expert level subnetting in no time. So speaking of time, thank you very much for the time you've invested in this video. I hope this has been informative for you, and I'd like to thank you for viewing. Default masks, classes, and private addresses. Let's jump in. I know your time is precious, so here's the gig. If you know the answers to these questions and are comfortable with what the correct answers are and why they are, you can go ahead and skip this video, and you know what? You and I can have just as much fun in the very next video. On the other hand, if you aren't as comfortable as you want to be with any of these questions, have no fear, we're going to cover each and every one of them in this video. So pause me right now, read these questions. If you want to go through this content, I am absolutely looking forward to it. When looking at IP version 4 addresses, there's three distinct groupings. They call them classes of addresses that we can work with for usable IP addresses for hosts. And they include Class A, Class B, or Class C. So here's what I'd like you to do. I'd like you to jot down on a separate physical piece of paper. I don't care if you use a pen or a pencil, but what I've discovered is that writing things down gives one additional sense as far as learning it, and it'll help you remember it. So the three classes of addresses are A, B, and C. Now the way you recognize a specific class of address is we look at the very first number before the first period right here. We look at the first number, and if it's in the range from 1 to 126, it is it's a Class A address. If that very first number is within the range of 128 through 191, it is a Class B address. And for our third category, our third class, our Class C, if the very first number is within the range of 192 through 223 inclusively, that would mean that that IP address, regardless of what's following, is a Class C address. And the cool thing is, we only have to look at the very first number before that first period to identify the class of IP version 4 address that it is. So here's what I'd like to do. I'd like to do a little exercise with you where you and I can identify, based on the first number in the IP version 4 address, whether or not it's a Class A, B, or C address. And to do that, let's go ahead and use the command traceroute, which on a Windows machine is TRACERT. We'll use the -D, that means I don't want to try to resolve every single router in the path to a host name. And then we'll put in the IP address of a Google DNS server at 8.8.8.8. And what I would like you to do as well is I would like you to do this same thing from your computer. And I just want to remind you that that -D on a Windows machine will save us a bunch of time because it won't try to resolve the IP address we find in the path to a name. So let's go ahead and press enter, and our first hop is my internal router at 192.168.1.1, and then we're going out to my service provider's network at 10.72.0.1, and then off to other internet routers at 24, etc. And it looks like the device at hop number 12, whatever it is, doesn't like feeding back the information regarding our time to live expiring, which is the way traceroute operates. So here's what I'd like to do. Let's go ahead and take this IP address right here, 192.168.1.1, which happens to be my first router in the path between myself and 8.8.8.8. And my question for you is simple. Is this address a class A, B, or C address? So take a moment, think about it. Is it a class A, B, or C address? Now you might be saying, oh, this is easy. I'm going to look at this chart over here. And you said, Keith, all I have to do is look at the very first number, which is 192. And 192 is in this range right here, which makes it a class C. You would be absolutely correct. Fantastic. Let's do yet another one. How about this one right here? This is 68.105.30.181. What is that? Is it a class A, a class B, or a class C address? And again, if you're saying, well, Keith, that's easy. I simply look at the very first octet only, the very first number in that IPv4 address. It's 68. I find out which range it fits into, and boom, it's a class A address because the number 68 is absolutely within that range of 1 through 126. Excellent, excellent work. And here's what I would like you to do right now. If you've done your own traceroute, which I hope that you have, I would like you to pick the fourth hop, whatever that is, the fourth hop in your own traceroute, and using that fourth hop, whatever IP address that is, I'd like you to identify, is that IP address that is your fourth hop, is it a class A, a class B, or a class C? Now, if you're on a device that doesn't have the ability right now to successfully do a traceroute, you can go ahead and use my fourth hop, which is 24.234.6.185. And once you've identified that as a class A or B or C address, again, based on that first number before the first period, you can go ahead and resume the video and we'll proceed. Meanwhile, go ahead and pause me while you work out the class of that address. It is really important to do these expert exercises as I assign them in this course, and I want to take a moment to personally thank you for investing that time to do that exercise. The next thing that I'd like you to do right now is on a piece of paper, I would like you to write out this table of classes. And it goes class A is 1 through 126, class B is 128 through 191, and class C is 192 through 223. What I want for you is the ability on demand to go ahead and write those three classes out. That way, if in any situation you need to remember what's a class A or a class B or a class C, the exercise that we're doing right now of having you write that out will assist you in measurable terms in remembering that first octet and the ranges associated with each class. So take a moment, pause me, and write that out right now. So thank you for taking that next step into mastering IP addressing. That's fantastic. Now, one of the questions that I get a lot is, hey, Keith, I see this is 1 through 126, and I see that class B starts at 128. What happened to 127? Well, in measurable terms, 127, an IP address that begins with that, really does fit into the class A address space. However, the 127.anything is a reserved loopback special purpose address. We can't assign that to an actual interface on like a computer or a router or anything like that. It's set aside for special purposes. So we can't actually use 127 in a production sense. The other question I seem to get a lot, and I want to talk with you about it right now, is why in the heck do we even care about if it's a class A or a class B or a class C address? And the reason we care is because there is a default mask, that identifier that tells us exactly how much of that IP address going from left to right, how much of that IP address is the network address. And that's the primary reason why we care. So let's write out some IP addresses. Let's say we have 10.1.2.3, and let's say we take a class B address, the first octet, the first number being, let's say, 130.6.9.250, and let's take a class C, and let's take 200.100.250. .4.5. So we have a Class A, Class B, and Class C address. The biggest reason why it even matters at all is because the default mask, which is controlling which part of the IP address is the network and which part is left over for the actual host, for a Class A, the default mask is the first number. With a Class B, the default mask is the first two numbers. So first number, first two numbers. And for a Class C, any guesses? And if you're saying, hey, Keith, I'll bet you it's the first three numbers with the Class C just because of the pattern, you would be absolutely right. And that, my friends, is important to know with IPv4 addresses. The default mask, which is associated with a Class A, which is different than the default mask associated with a Class B, and different also from a default mask associated with a Class C address. So here's the expert exercise that I'd like you to do right now. On a piece of paper, I'd like you to write out the following: that a Class A address uses the first number as network, which means that the mask is taking the first full number as the network address, leaving the last three numbers for host addresses. A Class B takes the first and second numbers as the network address, which leaves the last two numbers for host addressing. And a Class C address uses the first, second, and third number as the network address, which leaves the last number for host addressing. So take a moment right now, pause me, and go ahead and write out the fact that Class A has the first number as the network, Class B has the first and second number as the network, and Class C has the first, second, and third number as the network address. So let's go ahead and test what we've just learned and apply it. We're going to do another trace route, and we'll say don't bother doing the name resolution, and let's go out to 8.8.8.8 again, and we'll press enter. And as that completes, I'm going to do a Control C so it doesn't time out on that last one. Here's what I'd like you to do. Let's go ahead and take number 9 in this trace. So number 9 says 72.14.238.2. Now that represents, on the public routable internet, some IP address that's associated with a router on the internet. In fact, that router happens to be in the path between my computer and the destination of 8.8.8.8. And what I'd like you to do is tell me, with this address, 72.14.238.2, I would like you to tell me if we were using the default masks associated with Class A, B, and C, which portion of this IP address right here would represent the actual network address, and which numbers on the right would represent the actual host addresses. So I'd like you to take a moment right now, pause, and based on what we've talked about in this video, go ahead and answer that question. And then when you're ready, unpause me and we'll take a look at it together. So the way I would approach this, I would say, first of all, which class of IP address is this? Is it Class A, B, or C? The only thing we have to look at really for that is the very first number, which is 72. 72 falls in the range of a Class A address, and based on that, we also know that the default mask for a Class A address is taking only that first number. So this would be the network right here, and all of these numbers to the right, by default, would become the host addresses. So let's do it one more time. We'll choose a different IP address this time. Let's go ahead and choose this guy right here, 216.239.48.167. So 216.239.48.167. My friends, if we were using the default masks for this address, how much of this IP address would be the network, and how much of this address on the right would be the actual host address? Where would that dividing line be? So I can see the light bulb going on for a lot of you right now. You're saying, okay, Keith, I got this. This is 216 is the very first octet. 216 falls in a Class C address, and by default, for Class C, it's the first three numbers are the network. So the network address is 216.239.48, and the leftover portion, which isn't consumed by the mask, is the host address. And if that's what you thought, you are absolutely correct. For the defaults, you find out what class it is first, and then secondly, you apply the default properties for the mask for that address. In the case of a Class C, the first three numbers are the network address, leaving the last number for host addressing. Another thing that I'd like to share with you right now about talking about this network 216.239.48, again, if we were using the default mask, is how would we write that out? And what you could do is you could write out 216.239.48.0 when we're talking about the network. Because when we're describing just the network, we don't really care about host addresses. So everything to the right of the mask, if you will, you can go ahead and zero out when you're just talking about that street or that specific network. So we could say that this router is living, if we're using the default mask for a Class C address, that router is living on network 216.239.48.0. And his actual host address is 167 on that network. The next thing I'd like to chat with you about is terminology. Sometimes we'll hear the term of network or subnet. And really what that is a network is like a street on a computer network. And a subnet is like a subdivision of a street on that network. So very often when people talk about networks or subnets, from a loose perspective, we're really referring to the same animal. It's simply the street name for a given part of our network. So the last thing I'd like to chat with you about is private address space. Let's say, for example, we have the big cloud called the internet. And out there, we have a server, DNS server, a group of servers being represented as 8.8.8.8. Those are DNS servers from Google. Now, if they were using a default mask, which part of this IP address for their DNS, which part would be the network and which part would be the host? And if you're saying, okay, Keith, I got this now. It's a Class A address, fits in that range, and by default, the first number is the network. And again, if they were using that default mask, the last three numbers would be the actual host address. Fantastic. So how exactly does that relate to private address space? Well, let's say we have a little company called Acme Incorporated, and they've got several networks. So they have a little router, and they've got a network here, network here, network here, network here, and they want to start using IP addressing. Well, what's preventing them from using the 8 network? Nothing. They could absolutely have this be an 8 network right here. And they could have a PC on that network, and they could have full interconnectivity, maybe the 9 network and the 10 network and the 11 network, no problem. And they could have full interconnectivity inside of their environment. Well, what happens if they try to connect to the internet? Well, normally what's going to happen is we're going to have a router. So I'll label that as router. And that router is going to do something magical called network address translation, where it's going to swap out the source address, and these customers, as they go out to the internet, they can go ahead and appear as whatever globally assigned IP address the service provider is allowing that customer to use. So you might be asking, okay, Keith, what's the problem? Well, I'd like you to consider this computer right here, PC1. If PC1 believes that it is connected to the 8 network, and it is trying to reach 8.8.8.8, which is a Google DNS server, this little PC is not going to try to use its default gateway. It's going to think, oh, I'm trying to get to 8.8.8.8. It's on the local network. It's going to start ARPing, trying to resolve that IP address to a layer 2 address. It's not going to have success. And what's wrong with this picture is that this PC will never get out to 8.8.8.8 if this PC believes that the 8 network is local. So what is Acme Incorporated going to do? Well, what they can do and what everybody can do is use what are called private address spaces. Inside of the Class A, B, and C address ranges, they have set aside special IP addresses that we can use anywhere we want to, and we won't have to worry about colliding with somebody else's IP address space. For example, we won't use an 8 here, and there will be a globally addressable 8 there. It won't happen if we use private address space. And so here's what I'd like you to do. I would like you to write out on a piece of paper these ranges, which are the private IP address ranges that are commonly used for IPv4. In the Class A range, anything that starts with 10, boom, that first octet. If it's 10, that's the private address space that anybody can go ahead and use for their private networking. A Class B, we have a range of 172, that's the first number, and then 16 through 31. The numbers after that don't matter. So for example, on the 10 network, these last 3 numbers could be anything. With the Class B, 172.16 through 31, anything in that range. The last 2 numbers don't matter. It's still a private address. And then for a Class C, we have 192.168. Anything is also considered a private address space. And that's why in our IPv4 fundamentals video that we went through together, When you did an IF config on Mac or Linux or an IP config and looked at your IP address, it is very likely that if you're at a company or an internal network, it is very likely that you are using on your computer one of the IP addresses from the private IP address space. And again, to get out to the internet, we'll simply use network address translation to translate one of our private addresses into a globally routable address, so the internet doesn't really know what our internal private addressing space is. They'll simply see the address that we translated to during the NAT process. So take a moment right now with this expert exercise. Write out this private address space for Class A, Class B, and Class C. And when you have this table written out, go ahead and click on play. So here are the action items I would love for you to do. If you haven't already done the exercises assigned in this video, go back through and make sure that you do them. Remember, small and consistent steps are going to get us to that destination we want, which is mastering the idea of IP addresses and specifically custom subnetting with IP version 4. The other thing I'd like you to do is go back and take a look at the questions at the beginning of this video and walk through them and make sure that you're now comfortable with not only what the questions are, but the correct answers to those questions. I have had a blast. I'm so grateful for your time. I hope this has been informative for you, and I'd like to thank you for viewing. It's important to be familiar with the world of binary, and we're going to have some fun with that in this video. Let's jump in. To maximize your time, here's the opt-out questions for this video. Go ahead and take a moment, pause the screen, read those 3 questions. If you're comfortable with the answers to each of those, go ahead and skip this video. I'll see you in the next one. Otherwise, hold on to your seats because we are in for a ride. I'd like you to imagine that you and I have walked into a showroom floor. It could be cars or boats or what have you. And on one of the items that we're looking at, it has a price tag and it says this, 45,239. And I want to ask you, how much is that? And I'm not talking about euros or dollars or pounds. I'm talking about the actual number itself. Now you might be saying, well, Keith, this is really obvious. It's 45,239. That's the number. And how did you get that so quickly? And the reality is because we've been using base 10 numbering system for all of our lives. It goes something like this. We have several positions here. For example, the 9 is in the 1s position, and the 3 is in the 10s position, and the 2 is in the 100s position. The 5 right here is in the 1000s position, and the 4 is in the 10,000s position. And all we're doing, because we use a base 10 numbering system, is the first number is always a 1, and then the next position is times 10 and times 10 and times 10 and times 10. In fact, we could go all the way down, just continuing to multiply that placeholder by 10 by 10 by 10. And really, it was 4 10,000s. It was 5 1,000s. It was 2 100s. It was 3 10s. And 9 1s. But this is so second nature to us, we didn't have to break it out like that. In fact, when we count, for example, our numbers go through 0 through 9. So we have 10 distinct numbers to play with, 0 through 9. And when we count, we do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what do we do next? Oh, we're out of numbers. We simply carry the 1 into the next position, and we put a 0 here. So 1, 0 in decimal represents 1 10 and no 1s for a total of 10. And then we go to 11 and then 12. And then if we get all the way to, for example, 999 by continuing counting, and we need to go 1 more, we carry the 1 again. And we have 1,000. So that means we have a 1 in the thousands position, and we have 0, 100, 0 10s, and 0 1s. Now you might be asking, okay, Keith, I totally get this. This is base 10, the numbering system most humans on the planet have been using our entire lifetimes. So what has that got to do with this thing called binary? Well, binary is simply a different type of numbering system. Instead of using base 10, binary uses base 2. So with base 10, we had numbers of 0 through 9, which are 10 individual separate numbers. And with base 2, we have 0 through 1, which are a total of 2 separate numbers. With a base 2 numbering system, the first position over here on the right is a value of 1. And that's true for all the numbering systems that we use, whether it's octal or hexadecimal or decimal or binary. That first position has a value of 1. And then as we move left, this next position is simply this first number times the base. So in the case of binary, it's base 2. This would be 1 times 2. And I'll put that right here, and that'd be 2. And this next position over here, this next placeholder, if you will, is going to be this number times 2. So that would be 4. And as we go left, it would be this number times 2, which would be 8. And then times 2, 16. And times 2, 32. And times 2 again, which would be 64. And times 2 again, which would be 128. And how far could we go with that? The answer is we could go forever and ever. As long as there's numbers to use, we could continue to multiply that by 2. So with a base 10 numbering system, it went 1 and then times 10, times 10, times 10, etc. With base 2, we start with 1 and it's times 2, times 2, times 2, times 2, etc. It's also important to note that although we could go a really long way left here, we really only need to worry about 8 positions at a time when we're dealing with things like IP version 4. So here, my friend, is your very first expert exercise for this video. I want you to write out these value positions for binary. And again, the way to do it is you start on the right with a number 1, and then you simply take that number and multiply it by the base as you go left. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 64 times 2 is 128. And that, my friends, is what I would like you to do right now. So here's what I would love for you to be able to do. On demand, I'd like you to be able to write out this table of the actual weight values for each of the positions. On the far right, starting with 1, then times 2, times 2, times 2. You can also go the other direction by starting with 128, dividing by 2, dividing by 2, dividing by 2. That also works. And when you do this, if you're doing it on paper, when you write it out, to practice, go ahead and fold that part over so that when you do it the second time, you're not simply looking at what you did previously. Having this skill of writing out the binary weight values for the positions is an important skill. I wouldn't ask you to do it unless it was critical. So please take a moment and make sure that you can write this out on demand. So let's take a look at an example of how a binary number works. Now in binary, there's only 2 numbers that we get to play with, and they are a 0 and a 1. See, in decimal, we had 0 through 9, 10 different positions. In binary, we have 2. We have 0 and 1. It's sort of like a light switch. Either it's off or on. That's our only 2 choices. So if we had a binary number like this, that's 1, 0, 0, 0, 0, 1, 1, 0, holy schnikers, you know, what exactly is the value of that number to us as humans? And the way to figure that out would be saying, okay, well, we have a 1 in the 128th position, so that's 128, plus 0, because we have no 64s, plus 0, no 32s, plus, okay, how many 16s are we going to add to this equation? If you're saying, well, Keith, it's like a light switch, right? It's either on or off. Because this is a 0, it's off, which means we don't have any 16s. So we're going to say 0 there, plus 0. And here we go. In this third position, we have a 1 on in the position that's worth 4. So what would we add down here? And if you're saying, well, Keith, over here we had a 1 on in the 128 value, we added that. I imagine that if we would go ahead and add 4 for this position right here. And that is exactly right. So we'd add 4 there. And how about the 2? The answer is, yep, we have one of those. So we'll add a 2 as well. And then 0. And then it's simply a game of adding. All we're going to do, if we want to find out the actual value of this binary number, all we simply do is add these up. So it's 128 plus 4 plus 2, and that's it. So 8 plus 4 is 12, plus 2 more is 14. We'll carry our decimal 1 right there. That's a 4. 2 plus 1 is 3, and then we have a 1. And so the actual value of this binary number, 100000110, is 134. The key part that I want to make sure you have the ability to do is write out this table, if you will, of the actual values of the positions. That's the most important aspect. I would like to do one other exercise with you, and let's say we have a binary number of 0, 0, 0, 0, 0, 0, 1, 0. What is the equivalent value of that binary number? And again, to figure that out, you simply say, okay, we don't have any 128s, we don't have any 64s, no 32s, no 16s, no 8s, no 4s. We do have a 2, so it's going to be 2 plus, and we don't have any ones. So basically it's 2 plus 0, and that is 2. So last week, somebody at the office sent around a note, and it said this. It was very, very funny. It said, there are only this many types of people regarding binary. Those who get it and those who don't. And the reason that's funny is because in decimal, right, that 1 would be in the tens position. It looks like 10, as in 5 plus 5, a total of 10 people. However, in binary, that same number of 1, 0 is representing a value of 2. So there are only 2 types of people regarding binary, those who get it and those who don't, which makes the joke funny. And for those people who don't understand, binary is simply a t-shirt that they read and simply don't get. So the actual process of doing converting with binary to decimal and decimal to binary, I've got a separate video for you and I just for that. Our focus in this video is simple. I want you to be able to write out these 8 value positions from right to left or left to right on demand. Make sure you do it accurately regarding the binary base 2 numbering system. Our action items for this video are real simple to make sure that we can write out the values for the 8 positions in binary, starting with 1 on the right and 128 on the far left. The other thing I would strongly encourage you to do is once you can write out that table successfully and comfortably, go take a look at the opt-out questions that are at the beginning of this video, and that will help validate what you've learned in this video. I have had a lot of fun. I really appreciate your time. I hope this has been informative for you, and I'd like to thank you for viewing. Wicked conversion skills between decimal to binary and back. That's what this video is all about. Let's begin. This is the opt-out section for this video. If you are comfortable with the answers, the correct answers to these 3 questions, I'll see you in the next video. We'll have some fun there. However, if you are not yet comfortable with binary to decimal or decimal to binary conversions, and you've got about 12 minutes, you are in the right place. Let's go. I remember seeing The Wizard of Oz, and near the end, they pull back the curtain to reveal who really is acting as the wizard. And that's what I'd like to do right now with IPv4. Even though IPv4 it's represented as dotted decimal. Here we have 4 numbers right here, and they're separated by 3 periods to keep each number separate from the other one. What's really happening is that's just for us humans as a convenience. What's really going on behind the scenes is that each one of these numbers represents 1 byte of data. Now before you freak out and say, a byte of data, it's really just representing each number 8 bits, which go into 1 byte of data. So each of these numbers, 130, 16, 33, and 17, because each number makes up 8 bits, sometimes these numbers are referred to as an octet. And an octet is nothing more than 8 bits that are all represented together in the same grouping. So whether you want to call this first number the first number, or the first byte, or the first octet, all of those mean the same thing. So the trick is, if we wanted to convert for whatever reason, including the ability to do things like summarization and custom subnetting, we first have to be able to convert these numbers between decimal, which they're shown here, and binary. Or maybe we're given a binary number and we want to convert that back to decimal so we can go ahead and input it, for example, in a router or a computer. Now the great news for you and I is that in converting, if we needed to convert binary to decimal or decimal to binary, it's really straightforward because in either method we're going to first write out this table. Now we introduced this table in our video titled Beautiful Binary, so you already know what this table is and how to draw it from memory. If you don't, I strongly encourage you to go back and revisit Beautiful Binary. But that's our starting point. Now the question might come up, well Keith, what do I do first? Do I do decimal to binary or binary to decimal? Usually you're going to be given something and you need to convert it to the other. In this case, we have a decimal number that we're going to convert to binary. So we're going to do that one first. And it's really just a game. And I call it the Does It Fit game. And here's how we play it. We take a number, so we're going to first start with 130, and we're going to write it out. And all we need to do is take this very first number on the far left, 128, and ask ourselves the question, does it fit? Does 128 fit into 130? Yes or no? It's a binary question. If the answer is yes, we're going to put a bit on in that position. And we're also going to subtract that value of 128 from the number we're trying to convert. So the remainder of this is 2. 130 minus 128 is 2. So we take that remainder and we play the game again. Does 64 go into 2? No. Well, it might a fraction of the time, but we're looking for, does that number go in an entire time at least once? And if the answer is no, it doesn't, we put a 0 there, okay? How about 32? Does it go into 2? No, it doesn't, so that gets a 0. Does 16 go in? No, it doesn't, that gets a 0. 8, does it go into 2? Nope. How about 4? Nope. And then we get down to 2. Does 2 go into 2? And the answer is yes, it does. It goes in exactly one time. So we'll subtract 2 from it, and we are down to 0. So the question is, does 1 go into 0? And the answer is it does not. And so we're going to put a 0 there as well. It's sort of like accounting. If you love accounting with debits and credits, trying to get them to equalize, that's all we're doing here, is we're trying to whittle this number down to 0. Also, if you ever come across a time when the number you're looking at goes in more than once, like 2 times, there's a math problem somewhere. So again, we start on the left and we play the does it go in game, and if it does, we take the remainder and then continue working our way right. So this number right here, 100,00010, is 130 in decimal. So let's do one more together, and then I'm going to have you do your expert exercise with a number on your own. So let's go ahead and clear the page, and let's go ahead and do 16. The game is, we want to convert 16 into binary. We're going to play the does it fit game. So we're going to write out on our paper 16, the number we're after, and ask ourselves the question, does 128 go in? The answer is no, negative. Does 64 go into 16? No, negative. Does 32 go into 16? It does not. Does 16 go into 16? Woo! The lights go off. Yes, it does fit. So we take that number that we just put in, we subtract that from our number, we take the remainder, and we play the rest of the game. You can't stop playing until you've given all 8 bits in that octet or that byte. So 8 doesn't go into 0, nor does 4, nor does 2, nor does 1. This is our binary number that represents 16. It is 0001, 0000. And that, my friends, is also why, as humans, we input IPv4 addresses as dotted decimal. It saves us a whole bunch of typing. So we're going to input, when we configure routers and devices with IP addresses, we're actually going to put in the value of 16 for that second octet. But what the computer knows, or the router knows, is that this is the binary value of that second octet. So here, my friend, is your expert exercise, your first one for this video. I'd like you to take this number 33, and your mission, which I hope you accept, is to convert 33 into the 8-bit binary number that 33 is representing. So I'd like you to take a moment right now, pause this. Now, if you say, well, Keith, how do I start? What I would encourage you to do is start by writing out this table and then simply writing out 33 and playing the game called Does It Fit? So does 128 go in? Does 64 go in? Etc., etc. Every time it does go in, you put a 1 and you subtract that value from your number and play the game again, continuing on with the remainder. So go ahead and pause me right now, work out the binary equivalent of the decimal 33, and when you come back, we'll validate what that answer is in binary. So excellent work. I absolutely appreciate you practicing and verifying that you can do this on your own. This is a critical, fundamental skill that we're going to be leveraging inside of our world of IPv4 custom subnetting. So the game goes like this. 33 is right here. We say, does 128 go into 33? The answer is no. 64 doesn't go in. 32 does. So we're going to put a 1 there. We'll say minus 32, and our remainder is 1. 16 doesn't go, nor does 8, nor does 4, nor does 2, but 1 goes in cleanly one time, and our accountant is happy because we've had a 0 balance at the end, which is how it should be. So the decimal number of 33 is representing our binary number of 001, 00001. If that's the answer that you got, absolutely great job. I've got one more task for you as another expert exercise, and that is this. I'd like you to take 17, that 1 byte of data, and tell me what the equivalent binary number is for 17. Go ahead and pause me and do that now. So I know that some of you have already shortcutted this, which is perfectly fine if you're to that point. But the manual way, which is a great way to start if you're just learning this, is to say, okay, great, the number is 17. 128 doesn't go in, nor does 64, nor does 32, but 16 does. And the remainder is 1. 8 doesn't go, 4 doesn't go, 2 doesn't go, but 1 does. But many of you looked at 17 and said, you know what? I get this. 17 is 116 plus 1 more. All the rest are zeros. I'm done. And as you practice more and more with the converting of decimal to binary, your skills will improve. But it doesn't happen by accident. It happens based on practice doing the conversion. So I'd like you to do one more for me. And I'm going to have you do this entire IPv4 address on your own. And the number is this, 193.17.95.136. That is the number that I'd like you to convert. And you're going to do it one octet, one number at a time, converting those to their binary equivalent. If you've joined me for all of these videos in order and you've watched the prior 5 minutes, you should be able to calculate the binary equivalent of each of these numbers completely on your own. Go ahead and pause me now and convert this IP address into its binary equivalent. I want to thank you for taking the time to go through these expert exercises. As you practice more and more, your skills will measurably improve. Now, our next task is, what if we needed to convert a binary number that we're given in binary to decimal? Well, we already had a sneak peek at doing exactly that in our beautiful binary video. It's really, really simple to do. Let's say we're given a binary number of 101001111. As an example. How do we convert that to decimal, the decimal equivalent? Well, the answer is we're going to take everywhere there's a 1, we're going to take that value from the placeholder it's in and simply add them up. So we're going to add up 128 plus 32 more plus 4 plus 2 plus 1. So we can do that longhand, 128 plus 32 plus 4 plus 2 plus 1. 8 plus 2 is 10 plus 4 more is 14 plus 2 more is 16 plus 1 more is 17. There's our 1, there's our 7. Then we have in this column 3 plus 2 plus 1 is 6. And in the hundreds position we have a 1. So that value of this binary number right here is 167. And I put 167 equals 167. I guess that's a little bit redundant. So in converting from binary to decimal, we simply look for the ones and then add up the values of those positions for our equivalent total value. So now it's time for your expert exercise in converting binary to decimal. And what I'd like you to convert is this number right here into decimal. So go ahead and pause me. When you're done, go ahead and resume and we'll confirm our answer. All right, welcome back. Let's see how we did. So for this answer, which we'll call option number A here, we have 64 plus 32 more, plus 16 more, plus 4, plus 2, and that's it. So if we add all of those up, there's 4, 5, 6, 6 more is 12, plus 4 is 16, plus 2 more is 18, we'll carry the 1, there's an 8. So for the tens position, we have 6 plus 1 more is 7, plus 3 more is 10, plus 1 more is 11, that would be 118. And if that's what you came up with, congratulations, you have the ability to convert from binary into decimal. Now let me give you a couple more that I'd like you to practice with as well. Let's take this one right here. Well, 0, 0, 0, 0, 0, 0, 0, 0. I want you to do that one if you would, as well as this one, 1, 1, 1, 1, 1, 1, 1, 1. And one more. Let's have you go ahead and do 1, 1, 1, 1, 0, 0, 0, 0. And we'll call those A, B, and C. And what I'd like you to do is write out on paper what the decimal equivalent of A, B, and C is. And if you're saying, Keith, I think I've got the A, it's 0, you'd be absolutely right. It might take you a little bit longer for B and C, so go ahead and pause me while you do all three of those, write out your answers, and then click on resume, and we'll compare notes. Okay, welcome back. So let's take this first one, option A first. And option A is 0 plus 0 plus 0 plus 0 plus 0 plus 0. Okay, so A equals 0. Now this next one, we have some more adding to do. So we have 128. And here's what I'd recommend. don't just do it in your mind. If you're new to this, do it as we have in this video by writing out like 128 plus 64 plus 32, which is what this is all about. So for answer B, it'd be 128 plus 64 more, which is 192, plus 32 more, which is 224, plus 16 more, which is 240, plus 8 more, which is 248, plus 4 more, which is 252, plus 2 more, which is 254, plus 1 more is 255. So B equals 255. And you might say, well, Keith, you did that in your mind. You didn't even write that out. And that's because this is one of those values that you're going to see a lot of 255. And it's just because of raw practice with these numbers that I can do that in my head. Otherwise, I'd be writing it out. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. And for answer C, we have 128 plus 64 plus 32 plus 16. And if we add all that up, the long way, the short way, use a calculator, what have you, it's going to end up to be 240. If those are the three values that you got when you did the expert exercise on your own, before we compared notes, my hat's off. If you didn't get these three numbers, I would ask you to go back manually, like we did right here and here, and add them up once again, just to confirm that you're doing the conversion from binary into decimal correctly. Also, the valid range, if you will, for any octet, any number in IP version 4 is going to be between 0 and 255. It can't be any lower than 0, because then we're going into negative numbers, and it can't be any higher than 255. Because in an octet, if every single binary number is on, the maximum it can ever get to is 255. But I also, just with a little caution, also want to point out that 0 through 255 is actually 256 different numbers, because 0 indeed is a value. But the numerical high number you're ever going to see is going to be 255. Our action items for this video are to, number one, make sure we've practiced the binary to decimal and decimal to binary exercises that I assigned in this video. And secondly, I'd have you go back to the opt-out questions at the beginning. When you can now comfortably answer those questions in the opt-out section for this video, you are ready for the next video. I've had a great time. I sure appreciate you joining me. I hope this has been informative for you, and I'd like to thank you for viewing. The bits and bytes of the mask. Let's begin. Here are the opt-out questions for this video. If you can answer all 5 questions comfortably and correctly, you can go ahead and skip directly to the next video. For everybody else, you are in for a treat. We're going to identify the magic and mechanism behind the mask and how it identifies which portion of an IP address is the network and which portion is left over for host addressing. I'd like you to imagine that a friend walks up to you and in casual conversation they ask you, "Can you tell me," says your friend, "about a mask, exactly what it does?" And as you think back to one of our very first videos in this course, in fact, it was the video titled Fun with IPv4 Basics, we discussed the purpose of a mask and what it does. And my question is, do you remember the purpose of a mask? Now, if you're saying, ooh, Keith, I know, it absolutely identifies out of an IP version 4 address, it identifies which portion of that IP address is the network, and everything else beyond that is the actual host addresses. Specifically, the host addresses for that network. If that's what you're saying, that's excellent. If you need a brief refresher on the basic function or purpose of an IP version 4 mask, I would strongly encourage you to go back and review that video called Fun with IP version 4 Basics. Because in this video, you and I get to take what we already know and build upon it as a foundation. So here, my friend, are the details behind how the mask identifies which portion of an IP address is the network. So I ran ipconfig on my Windows machine, and this is what it gave me. It said my IP address is 192.168.1.15. Fantastic. So I broke that into binary just for display purposes. And the first number of 192, I put in red in binary here, 168 right here in blue, the 1 in green, and the 15. So there's the decimal notation that we normally use and the binary equivalent of each one of those. Now what I'd like to do is talk about the mask. There is also a 32-bit mask associated with each and every 32-bit IPv4 address. So in the output of ipconfig up here, it says that my mask, and that also brings me to a point of nicknames. For example, sometimes it's referred to as the mask, sometimes it's referred to as the network mask, sometimes it's referred to as the subnet mask, but any way you slice it, when we're talking about IPv4, it's referring to this device that identifies which portion, going from left to right, which portion of that IP address is the network and which remaining portion is available for host addressing. So this is how it does it. That 32-bit mask is also represented in dotted decimal. So I have the mask right here. There's 255.255.255.0. So that's the mask literally off of the computer that I'm using. For display purposes, I converted the mask octets into binary. So there's the first 255 and the second 255, the third 255, and of course this last octet of all zeros represents that decimal zero right there. So here's the magic. What happens is the computer lines up all the bits of the actual IP address with those same bits in the mask as shown here. And so here's what the mask does. We simply follow the bits that are on. The bits that are on in the mask is representing which portion of the IP address is the network. So if we simply follow the mask and the bits that are on and then stop when they stop, which in this case happens to be right here, that, my friends, is the dividing line. Everything to the left is the network, and everything to the right is the actual host portion. So in this case, we could say that my computer is on network 192.168.1, the first 3 octets, and that my host address is .15 on that network. And there's an additional little piece that I'm going to share that you don't really have to memorize, but some of you are going to be interested in it, so I'm going to share it. The way it actually determines this is by doing some multiplication. It multiplies the bit in the mask against the corresponding bit in the IP address. And if we did that, for example, 1 times 1 equals 1, and 1 times 1 equals 1, 1 times 0 equals 0, effectively, we're going to have the same exact number that we have up here down below. And so this one's going to be 10101000, and this third one is going to be 00000001. And the very last octet, what it's going to be if you multiply all those by 0, they're all going to be 0 no matter what. So if we converted this back into decimal, it would be 192.168.1.0. And that's how we represent networks inside of IPv4. And more specifically, we could put a slash here and say 24, which literally means that the first 24 bits, 8 bits here, and 8 bits here, and 8 bits here, those first consecutive 24 bits going from left to right represent the network, and the last 8 bits are available for host addresses, or like house addresses, on those streets. Now I've got a question for you. Why in the world can we just go ahead and say this is a 24-bit network, that the network is the first 24 bits? And the reality is, I'm not saying it. I'm just saying that the computer is telling me that's the fact of how this current computer is configured. The mask is the first 24 bits that are on, and that is what's telling me that this is a 24-bit network. It also implies that the last 8 bits, these bits right here, are available for host addresses on this network. I've got a little exercise I'd like you to do with me, and that is this. Let's pretend that this mask isn't this one right here, so we're going to replace that for a moment, and let's say that the mask instead is 255.255.0.0. So the mask in this octet would all be zeros, just like that. And here's my question for you. Now that we have this mask, what is the actual network address, if this is our mask, and how many bits of the IP address are being used for network, and how many bits are now available for host addressing on that network? So take a moment right now, go ahead and pause me, determine what you think the correct answer is for the actual network address, and then we'll compare notes. Awesome. Thank you for taking a moment to do that. So here's how I would look at this. I'd say, well, we're going to follow the bits in the mask until they stop, and then you can, draw a line. And everything to the left of that is the network, and everything to the right are the host addresses. So we could say that with this mask, the network is 192.168, and then anything beyond the mask, when we're identifying the network, we just zero out. So this is the 192.168.0.0 network /16. It's a 16-bit network, and we have another 16 bits available for host addresses on that network. Let's do one more exercise just like that, except this time, let's go ahead and change the mask, and we're going to make it 255.0.0.0 for our new mask. So this is going to be a 0 and a 0, and we're going to have all these zeroed out here as well. So now if this is what our computer showed us, now my question is, what is the actual network address that this computer is on? How many bits is it? How long is it? And how many host bits are available? So go ahead and pause, make your decisions, and then let's compare notes after you resume. Awesome. Thanks for taking a moment to do that. So here's one way we can approach this. We simply look at the mask first. That's the very first clue. And we're going to say, okay, this mask says that the first 8 bits are being used for the network. And if all the rest of the bits are zeros, that's the dividing line. And the cool thing is about a mask, it won't jump. This network mask or subnet mask or whatever you want to call it doesn't jump. It's not going to take like a bit here and a bit over there. They are going to be contiguous bits moving from left to right. So a mask will never say 110111. It's going to be contiguous. So because the dividing line is right here, our very first octet is the network. Everything after that is zeroed out from the network address perspective. And that's 8 because it's the first 8 bits representing the network. And now we have the remaining 24 bits of that IP address, which are now representing host addresses on network 192. So let's do one more example to help reinforce the concept. Let's say we have a Macintosh or a Linux or a Windows box sitting on a network, and it's a happy computer. You want to know why it's so happy? Because it's got an IP address. It's got the IP address of 10.25.3.99. That's its IP address. And guess what it also has? It also has a mask. That mask in decimal is 255.255.0.0. And what I would love for you to do right now is tell me what is the actual network that this computer is sitting on, what is the host address for this computer, and what is the number of bits that are currently being used by that network for network addressing, and how many bits are left over for host addressing on that network. So take a moment, go ahead and pause me right now, take as much time as you need, and once you've calculated what the actual network address is that this computer is sitting on, go ahead and resume me, and then we'll compare notes. Awesome. Welcome back. So in this example of 10.25.3.99, the very first thing we're going to look at isn't the IP address at all. It's the mask, because the mask is controlling which portion of that IP address is the network and which portion is available for host addresses. And the mask is saying, I'm consuming, I'll use green for this, I'm consuming the first octet for network. So we know that the 10 is part of the network address that the computer is sitting on. We also know based on the mask that the second octet is also consumed and being allocated for the purpose of network addressing, and that's it. The third and fourth octet, the mask isn't taking anything, so we can draw our dividing line right there. This computer is sitting on network 10.25, and then we simply zero out the bits that host addresses are going to have, 0.0 as we describe the network, and that is a total of 8 bits here and 8 bits here, a total of 16 bits being used for the network address. Now that also implies that we have 16 bits left over that are not being used for the network address portion that we can then use for individual host assignments on that network. So this computer with the IP address of 10.25.3.99, the first 2 numbers are the actual network right here, and the last 2 numbers of 3.99 represent the actual host portion, or this guy's unique identifier on that network regarding IP addressing. And as we mentioned, there's 16 bits being used for the network, and there's also 16 bits available for host addressing. So I've got one more exercise, and this one I'm going to have you do on your own with the computer that you're currently using. If you're on Windows, you can run ipconfig. What I'd like you to do is display your IP address and mask, and once you do so, I would like you then to write out what network is your computer currently connected to, and I'd like you to go ahead and include the number of bits of that network. And the only way to really determine that is by looking at the mask, seeing how long it is, how many bits it's taking, drawing the line. Everything to the left is the network, and everything to the right of that line is the space available for host addressing on that network. And that, my friend, is your homework assignment. I have had a great time. Here's the 2 action items for you. Number 1, make sure you do the expert exercises that I assigned, including the homework. And then secondly, go back, take a peek at the opt-out questions near the beginning of this video, just to validate that you now understand those topics and have the ability to go ahead and identify the network portion based on a mask of an IP address. I hope this has been informative for you, and I'd like to thank you for viewing. In this video, you and I are going to address stealing bits, host bits, and allocating them for network use, and moving the mask to represent that we've made a change in the network. Here's the opt-out section for this video. If you are comfortable with the answers to these questions and you know the finger game and how to calculate the number of bits to use for custom subnetting, I'll see you in the next video. For everybody else, you are in for a treat. Let's begin. I'd like you to imagine that you and I have shown up for work one day and our boss meets us with a big smile on their face and says, "Can you help me with a small project I'm working on?" And we say, "Sure, what do you need?" And our boss shows us this topology right here that they have drawn like on a napkin or something during a lunch. And they ask us, "Can you put this together? We have a pilot program we're doing and I want to just test some things. Can you make that all happen?" And we say, "Sure." We've got some extra gear, so we round up some routers and we connect them with switches. We even have a back-to-back serial connection that we put together. And then we go ahead and do the addressing. So maybe over here on this network that is common to R3, R1, and R2, we use the network 192.168.1.0/24. Now if we analyze that, that means that the first 24 bits of this number, which is the first 3 octets, are the network. And this last octet is available for host addressing. We've learned that in our previous nuggets in this course. And then for this network right here, between R2 and R4, maybe we use the 192.168.2.0/24. And for the network between R4, R5, and R6 right here, maybe we use the network 192.168.3.0/24. Now, once we've implemented these IP addresses, we go back to our boss all proud and say, "Hey, we're all done. Take a look." And he looks at it on paper and says, "Oh, I forgot to tell you something." And we say, "Oh, what's that?" And the boss says, "This kind of needs to fit into our existing network. And if you could," says the boss, "I need this entire topology to fit in this space of 192.168.5.0/24. I want to use that network to support this entire topology." Now at that point, we have a couple of options. One, we could say, this is only one network address. We have 3 individual separate networks that we need to deal with. Off of every router interface is a separate network. So we have network A, network B, network C. We could argue that we need more IP addressing space, or the other option, my friend, is to go ahead and do custom subnetting. The process of subnetting is simply taking an existing network space that we're given and chopping it up into smaller pieces. Sort of like if we had Sunset Street, for example. So if we had Sunset Street, which is a physical road somewhere in some town, and we needed to break that up into smaller sections, maybe we could have like Sunset Boulevard, Sunset Avenue, Sunset Lane, for example, and we can break it up. All we're doing when we're doing custom subnetting is we're taking one network address space, like the 192.168.5 network, and we are going to chop it up into smaller pieces so we can make additional smaller networks. Now, unfortunately, there is a price that's going to be paid if we take a perfectly good network like 192.168.5 and we chop it up. This network, which currently has 24 bits for the network and an 8 bits over here for the host portion, in order to do custom subnetting, what we have to do is we are going to say goodbye to a few good host bits. Those 8 host bits, which are over here, we are going to have to sacrifice some of them. Did I say have to? And the answer is yes. we are going to voluntarily take some of the bits over in this host portion from the network that we're dealing with, and we are going to allocate some of those bits over towards network addressing. And effectively what it's going to do is going to make more room for network address space, and we're going to use that additional space, those additional bits, to carve out additional subnets. So let's use a practical example here. Let's say we do have a 192.168.5.0/24 network, and we have to use that major network to go ahead and create additional space. The very first question to ask us in this scenario is, how many new networks, or new subnets, if you will, do we need to create for our topology? In this example, we need 1, 2, and 3. So step number 1, I'd like you to write this down with me, is identify number of new subnets needed, because that is the very first step. Identify the number of new subnets needed. So once you've got that jotted down, I'm next going to share with you how you can calculate how many bits you need to take. I'm talking about stealing bits from the valid host bits which are currently available, and we're going to sacrifice them to network address space. And that's done through something called the finger game. Now if you're wondering, Keith, what the heck is the finger game? You're not going to have to wonder too much longer, because we're going to play it together. I'm going to do this literally with you. So here's what I'd like you to do. I'd like you to look at your fingers, and I'll include your thumb in that discussion. So look at your fingers, and I'd like you to imagine that your fingers are bits. So if you hold up all your digits on your right hand or your left hand, and you look at them, how many digits are there? How many bits are there? And the answer for most people is going to be 5. Unless you're like my shop teacher in high school, but that's another story. So let's go ahead and use the presumption that most people are going to have 5 digits on their hand. And for this game, each of those digits represents a bit. So here's what I'd like you to do. I'd like you to go ahead and act like Fonzie from Happy Days. If you don't know who that is, I'll go ahead and walk you through this. You're going to make a fist with your right hand, stick it out in front of you, and then stick just your thumb up in the air. So with your thumb in the air, I'd like you to look at the back of your thumb, look at your thumbnail. I'd like you to imagine that somebody took a black permanent marker and they wrote right on your thumbnail the number 2. So look at it, see it. What kind of a font did they use? Is it clean? Is it sloppy written to? But see that 2 on the back of your thumb, and here's what we're going to do. If you only need 2 new subnetworks, all you need to do is steal or take a single host bit from the current available host bits to accomplish that. So the 2 is on your thumb represents that 1 bit, and that's the formula. Now in our case, we need more than just 2 subnets. So here's what we're going to do. With your thumb still up in the air, we're going to go ahead and bring up another digit, like your pointer finger, and when you bring that finger up, I want you to double the 2 on your thumb. So that goes to 4. The number that you verbally said is the number of subnets you can create. If you look at the number of digits in the air, which are now 2, that's how many bits it takes to generate that many subnets. Just for grins, that meets our needs. All we really need to do is take 2 bits, and that'll create 4 subnets, which meets our need of 3. So let's do this. Let's start from scratch, and let's see how many subnets we could create if we stole or took 5 host bits. So the game always starts like Fonzie. You make a fist, you put your thumb in the air, on the back of your thumb there's a 2. And the next thing we're going to do is bring up our pointer finger and verbally double that number to go to 4. And bring up another finger, so we have 3 digits in the air, and double the number to 8. Bring up another digit, double the number to 16. Bring up another digit, now all 5 digits are up, and double that number to 32. And I want to remind you what the importance of this game is, what the relevance is. If you look at your fingers, you've got 5 digits in the air. That means if you take 5 bits away from the host addresses and you allocate them for network addressing, you can have 32 brand new subnets by using the address space available in those 5 reallocated bits. And this finger game that we can use to calculate the number of bits or digits on our fingers to use to create a certain number of subnets is a very valuable skill that'll come in very handy for you. So in our case, we only need 3 subnets to support this topology right here. So just as a review, let's do the thumb game once again, and we want to make sure we're going to identify how many bits it takes to create up to 3 subnets. So we play the finger game by making a fist. We put our thumb in the air. There's a 2 on our thumb. 2 is not enough. We bring up another digit. We double that number to 4. And that means with 2 bits, represented by the 2 digits that are up in our hand, we can create up to 4 subnets. So that third step is to identify number of bits to sacrifice. And I do say sacrifice because they were available host bits, and once we sacrifice them over for network addressing, they will no longer be available for host bits. So in our case, we are going to sacrifice 2 host bits because that allows us to have up to 4 subnets, which meets our needs. 1 bit wasn't enough, and 2 bits gives us up to 4 subnets, which meets our need. And the fourth step, and this is the most important, is to go ahead and let everyone know. What do you mean, Keith? You have to let everyone know. You see, if we are going to change the rules and use 2 host bits for the network address, we need to make sure that all the devices on the network know about it. So what we're going to do is we are going to modify the mask. You see, for this network at the moment, the mask is only claiming the first 3 octets, the first 24 bits of the IP address space. But now, if we're going to use the additional first 2 bits of that last octet, we need to change the mask. And that, my friend, is how we communicate the details of using additional bits for the purpose of networking. We're simply going to move the mask that many bits to the right, and they're still going to be contiguous. So now it's going to be the first 24 bits here, plus the first 2 of this last octet. The new mask is going to be 26. Now, out of our beautiful IP address space, now we only have 6 host bits available left for host addressing, which is restricting us a little bit on that end. But now we have more address space to play with, so we can create up to 4 brand new subnets. So your expert exercise right now is to write out these 4 steps. And that is to identify the number of new subnets that you need to create. Use the finger game with a 2 on your thumb, with your fingers representing bits and doubling the number every time you bring up a new digit. Remember, start with a 2 on your thumb. And then once you calculate how many fingers are in the air that meet your requirements for the new number of subnets, you identify that. In our example, we only needed to take 2 bits. And the fourth step is to modify the mask to let everybody know about it. And that's moving the mask to the right by that quantity of bits. So take a moment, make sure you have those 4 steps written down. And what I would like you to do is go ahead and pause me, turn the paper over, and I'd like you to go ahead and from memory repeat those steps. If you need to peek over the other side as a refresher, that's perfectly fine at the beginning. But I want to make sure that you, on your own, know this exact process. When you've written these out and are comfortable that you understand the process that you should go through, go ahead and resume me. And I want to share with you one more technique that's really important regarding the moving of that mask, those 2 additional bits. Now here's one of the challenges that's going to come up when we move that mask from a /24, which it was, over to a /26, is that how do we actually represent that in decimal? Because when we work with IP addresses, we're putting in dotted decimal. So what does a /26 look like in dotted decimal? Well, the first 24 bits are good for the mask are 255, 255, 255. Now that's not new. We've already been through that in this course. However, what is new is how do we represent the first 2 bits of that last octet, these guys right here, for the mask that they are on? And the answer is we're going to go back to binary for that. This bit on and this bit on. So that's bit 25 and bit 26. And all these bits in the mask are now off. What would that be in decimal? Because that's how we're going to have to input it to the device we're working on, whether it's a router or a computer. And to figure this out, we already know how to do the conversion. From binary to decimal, we simply add the values. So we add 128 and 64, and that's a whopping total of 192. So for the mask in the last octet, we would put 192, and what that tells the router or the computer that you're on is that, hey, we're using a /26-bit mask. The first 3 octets are all taken for network addressing, and the first 2 bits of that last octet are also taken for network addressing. Now I can hear it already. Some of you might be saying, oh, I don't want to have to convert from binary into decimal every single time I put some type of a custom or non-default mask on an IP address. And I'm totally with you. And that's why what I would recommend you do is create this mask values table as well. So right when you sit down to start working with IPv4 subnetting, you should definitely write out this table right here, which is the weights of the various positions for 1 byte of data. And you should also jot down the mask values for each of those positions. For example, if we had a bit on in this position by itself and nothing else, that would be a value of 128. If we take 128 plus 64, that would be 2 bits on, it'd be a total of 192. If we had the first 3 bits on, for example, it would be 128 plus 64 plus 32, which is 224. And plus 16 more would be 240. And plus 8 more would be 248. Plus 4 more would be 252. At some point, if you work with IPv4 a lot, you're going to have these values up here absolutely memorized. But until then, what you could do is this. Simply write out this table. Write the weights first, and then simply write the mask values, which the mask values are going to be 128 plus 64 plus 32 plus 16, and that's that top row right here. So for example, if we're using 2 additional bits from the host portion like this, that would be the mask value. There's our dividing line, and we're set. If we had a situation where we needed to use 5 bits for custom subnetting because we had a requirement for 32 subnetworks and we needed to take 5 additional bits, it would look like this in binary. We'd take that one, that one, that one, that one, and that one. We would leave these last 3 bits for host addressing. The dividing line would be right here, and our mask value would be 248. And if you needed to, you could manually calculate that. 128 plus 64 plus 32 plus 16 plus 8. But having this table here is very, very handy. So here are the 2 things that I want you to take away from this video. Number 1, I want you to be comfortable with the idea that we are stealing, we are taking away available host bits and sacrificing them for the purpose of creating additional networks. What used to be host bits, what used to be a large group of host bits are being whittled away from the high end and being sacrificed over for network addressing. The other thing I want to make sure you're comfortable with is quantity. How many bits do we need to take in order to create a certain number of subnets? And that's all about using the finger game. And to confirm that you get that game, here's what I'd like you to do right now as an expert exercise. I'd like you to do a scenario where you need to create 42 new subnets. So here's my question. If you needed to create 42 brand new subnets, how many host bits would you have to sacrifice to meet the need of 42? And the cool thing is this. This concept applies to Class A or Class B or Class C addresses, because maybe you have a 10 network that's starting with an 8-bit mask, or a 172.16 that's starting with a 16-bit mask, or a 192.168.5 that's starting with a 24-bit mask. It really doesn't matter, because all we're doing is we're stealing subnet bits from the current host portion. So in a network that had an 8-bit mask, we would start stealing the bits from this octet right here, because that's where the host bits start. In a 16-bit network, we would start stealing host bits from this 3rd octet, because that's where the host bits start. And from a network that had a /24-bit mask, we would start stealing the actual host bits from the host bits portion, which in this case is the 4th octet that we would begin stealing from. The actual quantity calculation doesn't change. It's all a matter of how many bits this is going to take to create a certain quantity of subnets. So here's what I want you to do right now. Go ahead and calculate using the finger game. How many host bits are we going to have to sacrifice to network addressing in order to get 42 subnets? Go ahead and pause me right now. Go ahead and do the finger game. If you're in a cubicle and people can see you, it's perfectly okay. Get those fingers flying, starting with that 2 on your thumb. So go ahead and pause me and do that now. All right, so let's see how you did. I'm going to go ahead and I'm going to do my thumb in the air right here, and this is going to be my fist. And on the back of my thumb, I've got the number 2. So that's where we start the finger game, is a number 2 on the back of our thumb. So our goal is to get up to 42. That's how many new subnets we need. So we put our thumb in the air, we say 2, that's not enough. We bring up another finger, and we go to 4. That's not enough. We bring up another finger. We go to 8. That's not enough. We bring up another finger. That's 16. That's not enough. We bring up another finger. That is 32. And that is not enough. So if we sacrificed 5 bits for custom subnetting, we would only get 32 subnets, which isn't enough. So what do we do in this situation? The answer is you keep that one hand with all 5 digits up, and you bring up the other hand and continue to double. So on our other hand, so I'll bring up another finger there, and we go to 64, and we stop, because 64 will meet the requirement of 42 subnets. And here's how the counting goes. We have 1, 2, 3, 4, 5, 6 digits in the air. That means we need to take 6 bits. And 6 bits will create for us 64 subnets. It's kind of a funny little game, but it's a great way to consistently get that information right. How many subnets do you need to create? How many bits will it take using the finger game, and then changing the mask to reflect that. So if we're taking 6 more bits, let's apply that to changing the mask. In the case of a current mask of 8, the new mask would be 14. We're simply adding 6 bits. In the case of 16, the new mask would be 22. 16 plus 6 more. And in the case of 24, the new mask would be 30. So to represent those 6 bits, it would look something like this. 1, 2, 3, 4, 5, 6. That's the new mask. We put the dividing line right there. And the new mask would be 252. So the new mask for the second octet for this network would be 252. The new mask for the third octet would be 252. And the new mask on this network, the 192.168.5/30, that would be in the fourth octet, the mask would be 252. It's representing on each of those networks that we're stealing the additional 6 bits and allocating them for network address space. And the concept is the same for each and every one of them. In the next video, I'll walk you through how to go ahead and determine the actual values of those additional subnets. All right, here's the action items for us in this video. Number 1, if you haven't already done the expert exercises, which absolutely include the finger game, I would strongly recommend you practice that and make sure you can do those calculations. Secondly, before you leave this video, go back and revisit the opt-out questions near the beginning just to verify that you can now answer those questions and that you are comfortable with them. I appreciate the time that you've invested in this course with me. I've had a great time. I hope this has been informative for you, and I'd like to thank you for viewing. IDs for new subnets. Every person really needs a name, and our new subnets need a new number. In this video, we'll identify exactly how to identify the new subnets you create and make it a simple process. Here are the opt-out questions for this video. If you can comfortably answer these 3 questions correctly, please join me in the next video. For everybody else, you're in for a treat here as well too. We're going to identify a simple and concise way of identifying the new subnets created when we're stealing host bits for custom subnetting. Let's begin. In our previous video together called Stealing Host Bits, we identified a couple of cool tricks. Number 1, we used the finger game to calculate the quantity of host bits to steal. We also identified how we can move the mask to tell all the network devices that we are playing by the different rules. Our next challenge is, what exactly are the new subnet numbers that we are creating? And to do that, let's do an example. Now, most of the first part of this is a review from things that we've seen in our previous videos together. So let's take a network of 10.0.0.0/8. And my question for you is, what does that 8 represent? Now, if you're saying, okay, Keith, that's easy. 8 represents the fact that the first 8 bits of this address right here that we're looking at represents the network, which also implies that the last 24 bits are all host addressing space. That is perfect. My other question for you is, what would this mask look like in dotted decimal? And if you're saying, okay, Keith, that's easy. We had that in a previous video in this course as well. That would be 255, which represents 8 ones for the mask, and then 0.0.0, and that is the mask in dotted decimal. Fantastic. Perfect. So here's the task I'd like to go ahead and give us. If we needed to create subnets for this topology right here, and this topology has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 subnets that we need to address. And we need to make it all fit inside of the space of 10.0.0.0/8. Everything that you see in this topology has to be within this boundary with an 8-bit mask. So my question for you is, how do we go ahead and do that? Now, we've covered this in our video called Stealing Host Bits. And the reason I mentioned that video is that's the first thing we need to decide. How many host bits do we need to steal or reallocate from the host portion? So right now we have 24 host bits. And we need to sacrifice a few of those to create subnets. And my question is, how many of those 24 host bits do we need to sacrifice to create up to 12 subnets? And my friend, to solve that, you simply play the finger game. We also discussed the finger game in the previous video called Stealing Host Bits. So I want you to pause just for a second and calculate right now how many bits, how many host bits would we have to reallocate or give away to the network address space to create up to 12 subnets. Okay, fantastic. So we need to steal 4 host bits. See, 3 wouldn't be enough. 3 would only give us 8 subnets. By stealing 4 host bits, we can get up to 16 subnets, which meets our requirement. So then the question is, what would the new mask be? The original mask is a /8. We're stealing 4 more additional host bits. Those are going to come out of the second octet in this example, because that's where our host bits are starting. And so if we stole an additional 4 host bits and allocated them to the network address space, what would the new mask be that identifies where that new boundary is? Now, if you're saying the new mask would be the old mask plus the 4 additional bits, which would be 12, you are absolutely correct. That's fantastic. And all of that we just did, we have learned in our previous videos in this course. And now, my friends, it's time to identify what the actual subnet IDs are going to be for those new subnets. Now, by stealing 4 bits, we actually are going to have a possibility of 16 new subnets. So we're going to have 4 left over that we're not using because we only need to go up to 12. And that's perfectly fine. But what exactly are those subnets? And to solve that, this is a fun part. To solve that question of what exactly are the subnets for this guy and this guy and this guy, all we're going to do is these 2 simple rules. And let's start with number 1. We are going to, first of all, determine the block size. Now, the block size, and I affectionately refer to it as BS sometimes, just because the shock factor sometimes reminds people to go ahead and look for it. The block size is nothing more than the least significant bit of the new mask. Whoa, Keith, stop the truck. What do you mean the least significant bit of the new mask? Well, if you take a look at these 4 bits that are on, and we're looking at this second octet here, if you look at these 4 bits in the mask, which one is the least significant, has the lowest value? And you might be looking at it and say, well, Keith, it's obvious. If we look at each of these bits, the very least one, the one that has the lowest value, is this guy right here, and that is the new block size. And what I'm going to have you do, if you've written this out, which I would encourage you to do every time you're working with IPv4 subnetting these weights, I would have you put a square around that number. So wherever the least significant bit is of the mask, I'd like you to put a block around that value, and that is your block size. In this case, it's 16. If we were stealing 5 bits, it would be 8. If we were stealing 7 bits, it would be a 2. So the least significant bit, we've determined the block size, in this case, is 16. Now, how is that going to help us? This part is almost magical. What we're going to do is we're going to begin at 0 and then simply add the block size. So for step number 2, in this example, let's go ahead and take 0. Now, that's really easy to get to. That is our first subnet, and sometimes it's called subnet 0. So that's our very first subnet, is subnet 0. And then for our next subnet, we simply add the block size. So it's 16, so we add 16 to this. That is our second subnet. And the third one, we're simply going to add the block size again. So plus 16 more is 32. That's our third subnet. And then we're going to add 16 more again. That makes 48. Now don't go doubling these. We're just adding the block size. So take care that you don't start doubling numbers and such, because we're just adding the block size for every new subnet. So that's our 4th subnet. And our next one's going to be 64 for our 5th subnet. Again, we're simply adding 16, and we simply add and add and add and add. And if we added 16 again, it would be 80. So that'd be our 6th subnet. So now as we look at these subnets, what's the problem? Well, they don't really look like subnets, do they? They just look like a digit or a couple digits, and they're not really in the format of an IPv4 address. So here's how we complete the picture. See this first network of 10.0.0.0? The new mask is going to be 12. All we're going to do is we're going to bring that same network that we started with up, 10.0.0.0. We have the new mask /12, and guess what? That is subnet 0. That is our first network. And that means that in this second octet right here, we haven't added a block size to it. That's our starting point. So subnet 0 looks like the original network with the new mask. For the next subnet, we're going to add that 16. So it's going to be 10.16.0.0/12, and that's our second network. And then 10.32.0.0/12. And that's our third network. And then 10.48.0.0/12. And it's important to put the mask on there so that you can communicate exactly how many bits are being used for the network, and the remainder bits are host bits. And then we have 10.64.0.0/12 and 10.80.0.0/12. And if we continue this process, we would actually get up to a point where we have 16 possible new subnets because of the 4 bits that we're stealing. And the reason I showed you this first without including it inside the IP address is I wanted to show you a process that is simple to follow. And that is, you identify the block size, put a little square around it to remind you, hey, this is the block size. You begin at 0, which is subnet 0, which looks like the major network with just a longer mask. And then you simply add that block size to the appropriate octet. So because here we start with a /8, and we started slicing and dicing in this second octet, that's exactly where we're going to add the block size value. So let's do another example, and I want to do it from start to finish each time so that you get in a rhythm or a pattern of exactly how to do this. Let's say that we want to have this network here, still 12 subnets, and we want to make it all fit in the address space of 10.50.0.0/16. That's our starting point for all of our new networks. We're still going to be stealing 4 additional bits because the actual quantity of subnets hasn't changed. Our new mask is still going to look like this with the dividing line right here, except now we're starting to steal against the host bits, which are in the 3rd octet instead of the 2nd octet. And that's because the 16 bits we're starting with indicate our starting point for the already allocated network bits. So here's what I'd like you to do. I'd like you to do these 2 steps. This is your expert exercise right now. I'd like you to determine the block size based on us using 4 additional bits for custom subnetting. And I'd like you to list out on paper the first 6 subnets that we would be using on this topology. All right, for those of you who are able to do this on your own, that's great. This does take a couple of practices to get the hang of it. So our subnets are going to be right here, determine the new block size, which is 16. So you're going to put a block around that to remind you that that is the block size. You're going to begin at 0, and here's our subnets. They are 0, and 16, and 32, and 48, and 64, and 80, and 96. 1, 2, 3, 4, 5, 6, 7. Okay, so that's the first 7 subnets. Now, what exactly are those going to look like as far as network addresses? Well, the first one is going to be 10.50, because those were already locked in stone before we got there. That's what we were given. And what we're doing is we're stealing the first 4 bits from the 3rd octet. So subnet 0 looks like the parent, I call it the parent network, and it looks like the same exact network except for the longer mask. The mask was 16. We're stealing 4 more bits. The new mask is now going to be 20. The next subnet is going to be 10.50.16.0/20. And the next one is 10.50.32.0/20. And it's just going to continue all the way down. So in a topology diagram like this, we might just say in the documentation that this is the 10.50.x .0/20 network. Then for these subnets, instead of writing out the entire subnet address, we might just put the value of X. For example, this is subnet 0, this is subnet 16, this is subnet 32, this is subnet 48, etc. And then somebody looking at the topology, you could say, oh, this is the network 10.50.0.0/20, this is network 10.50.16.0/20, and so forth. This time, let's mix it up a little bit more, and this will give us another opportunity to review the process and make sure that we have it down pat. In this case, let's say we don't need 12 subnets. Let's say we just need 6 subnets. So 1, 2, 3, 4, and 5, and 6. So all we need is 6 subnets, and we want to make it all fit within 25.35.65.0/24. So that's our starting point, is that 24-bit network. We need to make this all fit. So my question is, when we're given this, the very first thing that you'd have to do is what? What's our very first step? Now, when I look at this, it's like a game. It's like we have to find out some value first. And the first thing we really need to calculate is, okay, how many bits do we need to steal? Right out of our video called Stealing Host Bits. How many host bits do we need to take to create up to 6 subnets? And the answer is 3. So we play the finger game, we determine that we need to take 3 bits, and we are going to change the mask by increasing it by 3. So it would visually look like that. All the rest of the mask for that octet, in this case the 4th octet, would be zeroed out. And the new mask, because we're using 3 more bits, would not be a /24. The new mask would be a /27. So that's all the finger game in calculating what the new mask is going to be and how many bits we took to get there. And now, my friends, it's time for your expert exercise. What I would love you to do is these 2 things. Determine the block size, and then secondly, I'd like you to identify all 6 subnets that we would need for this topology. So pause me right now, take a moment, work through that, and then when you're ready, we'll compare notes. So here's the process that I would go through in solving this. I literally would. If you were watching me sitting at a desk and actually going through this, I would have written out the weights. Now, I do have a lot of it memorized, but on an average day, I would write out the weights, and I'd say, okay, great, my block size is 32, because that's the least significant bit of the mask, the new mask. And I would say my subnets are 0, because that's where we always start. And the next subnet would be 32 more. And the next subnet would be 32 more. And the next subnet would be 32 more. And the next subnet would be 96 plus 32. And we can just add that up. 96 plus 32. That'd be 8. And that'd be 12, which is 128. When in doubt, do the longhand math to make sure you have the numbers right. And plus 32 more. That's a 0. That's a 1. And we actually have a couple more, because with 3 bits, we can actually create 8 subnets. But we're only going to use the first 6. So the literal subnets would be 25.35.65. That's what we started with. And remember that first subnet, which is called subnet 0, it actually looks like the major network, but it has that new mask of /27. And the next subnet would be x.x.x. There's no reason to repeat the first 3 octets, because we can assume those are not changing. And the last octet is going to be 32/27. And then we have 64/27. And these are our new subnets. So over here, for example, in our topology, we could just write out, this is the 25.35.65.x/27. And this is subnet 0, subnet 32, subnet 64, subnet 96, and so forth. The secret, my friend, is all about the block size. Don't get caught up in the actual numbers of the IP address. Get caught up in what the actual least significant bit of that mask is. That will show you the block size, and then you can identify all of your subnets based on the block size. The BS, in this case, is the most important aspect of determining your subnets. So I'd like to do one more with you, and I'd like to go a little bit abstract. Let's say we have a network that is a /16. So forget about the first 2 octets. Whatever they are locked in stone. We are dealing with now the 3rd octet, as we're going to start stealing bits. And let's say for the purpose of this discussion that we need to steal 5 bits from host addressing in that third octet. And that would allow us to create up to 32 subnets. So our dividing line is right here. And my question for you is this: what would the new mask be if we're stealing these 5 bits? And what would the first 5 subnets be? And again, it really doesn't matter about these first 2 octets because they're going to stay the same for the entire discussion. It's really all about the third octet where we're splitting and slicing and dicing the bits for subnetting purposes that we need to pay attention to. So again, what's the new mask and what are the first few subnets? Go ahead and pause me and work those out right now. So thank you for taking time to work through that. What is really cool about this process is that it's the same. We're going to go ahead and first of all determine the block size. In this case, the least significant bit is in the position of 8. So that's our new block size. The subnets are going to be 0. Again, we're in that third octet because the first 2 are already chewed up. So our first subnet is going to be the 0 subnet. The next subnet is going to be the 8 subnet. And then we're going to have 16. And then this is for some, this is a little bit of a challenge, but only add 8 again. Don't go doubling. This is just adding the block size, adding the block size, adding the block size. So this would be 24. And this would be 32. And of course, we have another octet out there, so we'd have to hang that guy off as well. And then the new mask, what's that going to be? The original mask was 16. We're taking 5 additional bits. So 16 plus 5 is a /21. And if we had to write out that mask in dotted decimal, it would be 255, which means the first octet is all network. 255. The second octet is all network. That was that way before we got here. And what we've done is we've stolen 5 bits from that third octet. And to represent that, it would be 128 plus 64 plus 32 plus 16 plus 8. Or, and we have 248 already written for us, we could just say it's 248. Any way you want to get there is perfectly fine. It's just math. And then the last octet is all host bits. So the host bits available are the 3 host bits from this third octet plus all 8 bits from the last octet for a total of 11 host bits available. Our action items in this video are really simple. Number 1, make sure you've gone through the expert exercises with me, that you can now identify the actual block size and the subnets that would be available when doing custom subnetting. Secondly, I'd have you go back and take a look at the opt-out questions at the beginning, because now, after working through each of these exercises, you should be comfortable and able to answer the questions in the opt-out section for this video. I have had a great time. I appreciate the time we have spent together. I hope this has been informative for you, and I'd like to thank you for viewing. In this video, you're going to learn how to identify the range of valid IP address that we can actually assign to hosts on each of our new custom subnets. And here's the opt-out questions for this video. If you can answer all 4 correctly and you're comfortable, I'll see you in the next video. For most people, however, we are going to have a fantastic time right here, right now, as we identify how to quickly and easily identify the range of valid IP addresses on any of our given subnets. Let's begin. In our previous video together, we identified the individual subnets that can be created, and in this video, we're going to focus on the valid hosts that would fit on those subnets. So to do that, let's go ahead and use an example of this topology. We have 3 subnets that are required so far. Let's add a few more. Let's add a network out here, 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 and here. So we'll need a total of 1, 2, 3, 4, 5, 6, 7 subnets. So let's say we have a /24 network to begin with. So x.x.x.0/24. Now, do you get it that these first 3 numbers are going to be the same across the entire board if this is our major network? So we're going to start from that point. We're going to start stealing bits from the host portion, which is the last 8 bits. So by using the finger game, we can calculate that we need to steal 3 bits. That will give us up to 8 subnets, which is enough for our topology right here. So our new dividing line is right there. Our block size is 32, and our subnets are going to be subnet 0, subnet 32, subnet 64, subnet 96, subnet 128, subnet 160. Again, we're just adding the block size to each one of these. Subnet 192, and subnet 224. So here are 8 of the possible subnets that we could create. We're only going to need 7 of them. So over here, for example, we could have this be subnet 0, this could be subnet 32, this could be subnet 64 right there. This could be subnet 128, subnet 160, subnet 96, I didn't mean to leave him off, and over here subnet 192. So those are our subnets, and of course the first 3 octets would be XXX, meaning they would be whatever they were over here, followed in the last octet by this value. So let's say we've identified these subnets, we know where we're going to put them, and we want to go and configure an interface. For example, let's take a look at serial 0/0 on router 2. We go into interface configuration mode, we want to configure the actual IP address, and then we realize, oh my goodness, what are the valid IP addresses that are on subnet 128? And the focus of this nugget, this video, is to go ahead and walk you through the very straightforward process of identifying exactly what the valid IP addresses are for subnet 128. And the process is right here. You're going to start by listing the subnets. So here we have all 8 subnets. And I have the S in plural because you don't have to list all the possible subnets. You can just go ahead and start listing the ones that you're going to be using or the ones that you're concerned about. And again, we're going to use the block size to determine our subnets. Once we have the subnets listed, and we're interested, for example, in the range, let's go ahead and take subnet 128 as an example. The very first host, the first valid host IP address on a subnet is going to be that subnet plus 1 in the very last octet. Now in this case, we're already in the very last octet right here. So for the 128 subnet, the very first host is going to be 129. So I'll call this column right here first host. Now I want to ask you a question. If 129 is the first host, do you think 130 is also a valid IP address on this subnet? If you're saying, yeah, Keith, it sounds like it would be. It's right next to it. How about 131 and 132 and 133? And if you look at the numbers, everything that is lower than 160 is part of the 128 subnet. If we go high enough, we're going to bump into subnet 160. And the reason that's important to know what the next subnet is that the range of IP addresses on the 128 subnet will never go as high as 160. Why is that? Because 160 is the next subnet. So if we wanted to calculate all the valid IP addresses on the 128 subnet, the very first host would be the subnet plus 1, and the very last host is going to be the next subnet right here. I'd like you to read this with me. The last host is going to be the next subnet minus 2. So if this guy is 160, if we subtract 2 from that, the last host on the previous subnet is going to be 158. Now, the first knee-jerk reaction is, why? Why do we have to subtract 2? Why can't we just use like the next subnet minus 1? And the reason for that is the next subnet minus 1 is the broadcast address for the previous subnet. So the first host is this column. The last host is right here, and the formula for that is the next subnet minus 2, and the broadcast address is going to be the next subnet minus 1, which is 159 in this case. So what that means to us, if we want to configure the IP addresses here on subnet B, which is more specifically subnet 128, the valid IP addresses that you and I could choose to use for any device on this network, and I'm laughing because there's only 2 here, but the range of IP addresses could be anywhere between 129, so x.x.x.129, through 158. We couldn't use 128 because that's the actual street name all by itself. That is the subnetwork address. First valid host is 129, last valid host is 158, and regarding this subnet right here, the broadcast address that we would associate with this subnet is 159. One more IP address higher, and we're looking at the next subnet. So let's play that game again. And what we're going to do is we're going to use this formula right here, and let's pick on this subnet right here, subnet 192. So my question for you is this. What is the first valid host on the 192 subnet? What is the last valid host on the 192 subnet? And what is the broadcast address for the 192 subnet? So on the 192 subnet, the rule is that the first host is the subnet itself plus 1. So for the 192 subnet, that means the first host would be 193. The last valid host on this subnet is going to be the next subnet minus 2. Well, the next subnet is 224, so minus 2 would put our last valid host at 222. And the broadcast address for this 192 subnet is the next subnet minus 1, which is 223. That's it. That's how you calculate the valid range of IP addresses on a given subnet. So what I'd like you to do right now as your first expert exercise in this video is I'd like you to write down these 4 steps. List the subnets. The first host is the subnet plus 1. The last host is the next subnet minus 2. And the broadcast address is the next subnet minus 1. As you get more and more experience, you're going to be able to take additional shortcuts. But if you're new to this, having this process in mind of exactly what to do first, what to do next, that will assist you in identifying the valid host addresses on a given subnet. So take a moment, pause me, and write out these 4 steps right now. So let's you and I do another exercise. For our requirement, let's say that we have a /16 to begin with, and it really doesn't matter what those first 2 octets are. If the initial mask is 16, that's what the initial mask is. And let's say we have a requirement to create 15 new subnets. What I would like you to do is I'd like you to go ahead and list the first 4 subnets and their ranges. The ranges for a valid host address on those first 4 subnets. And for bonus points, go ahead and include the broadcast address for each of those subnets as well. So just to be clear, we're starting off with a /16. You need 15 new subnets. You're going to list the first 4 subnets and their ranges of valid hosts. Go ahead and pause me and do that right now. All right, welcome back. I'm curious, how did you do? Were you able to put all the pieces together? Here's how I would approach this. I'd say, first of all, we have this /16 network. Great. We need 15 new subnets. So, of course, we're going to do the finger game to identify how many bits we have to take away from host addresses to create at least 15 new subnets. The answer to that is 4 fingers, or 4 bits. And that new mask would look like this. There's our dividing line. There's our block size of 16, and the first 4 subnets would be 0 for subnet 0, 16, plus 16 more is 32, plus 16 more is 48, and that's all I asked for. It was the first 4 subnets. Now what's different about this than the last example is we are working in this 3rd octet right here. So this byte of data that we're cutting into, the host portions, represents the 3rd octet in this network that began with a 16-bit mask. So our new mask, it was a 16, so the new mask is going to be a /20, and I'm going to bring those subnets down here. We have x.x representing the first 2 octets. We have .0 and x.x.16 and x.x.32 and x.x.48. Those are our first 4 subnets. Now because we are in the 3rd octet, we have another 8 bits to represent over here that are all host bits. So a total of 12 host bits. These 4 here from the 3rd octet, plus all 8 bits from the last octet for host addressing. Now I did throw you a little bit of a curveball because we are no longer in the last octet. We are in the 3rd octet that we're actually stealing bits from. So if we wanted to calculate the first valid host address on these subnets, how would we do it? And the answer is the same exact way that we did it before. Our first task is to list the subnets. Well, here's the first 4. That's done. The first host is going to be the subnet plus 1, and we add that plus 1 to the last octet. So this network of x.x.0.0, the first valid host, I'll write first here, is going to be x.x.0.1. That's our first valid address. The first valid address for the 16 subnet, I'm going to leave off the x's, by the way. I'm just going to leave an arrow down there. The first valid host on the 16 subnet is going to be 16.1. The first valid host on the 32 network is going to be 32.1. And the first valid host on the 48 network is going to be 48. And you got it. We're just simply going to add 1 to the last octet, 48.1. So piece of cake! We've got the first valid IP address on each of those subnets. The next question, what is the last valid IP address? Or we might even want to go for the broadcast address first if you want, and then we could simply subtract one more from that for the last. It really doesn't matter in which way you do it, as long as you're comfortable with the process of what you are doing. So let's say for the 0 subnet, that's right here. Our first subnet is subnet 0. The first valid host address is 0.1. And I think the broadcast address is going to be the next subnet minus 1. You know why I think that? Because that's exactly how that works. Right here. The broadcast address is the next subnet minus 1. So if we wanted to look at the next subnet, which is 16.0, what is 16.0 minus 1? It's going to look like 15.255. And let me show you that in binary. In the third octet, we have 4 bits that are on. And then in the last octet, we have 8 bits that are on. So that is 15, and that is 255 right there. And our mask is right here. So my question is, what happens if you add one more, plus 1 right here? Well, all of these are going to carry over. So the plus 1 is going to topple all of these to zeros. This is going to turn to 16 because they're all going to topple over. And that's the binary behind it. So 16.0 minus 1 is 15.255. You simply put 255 for the last octet, and you take this number and say minus 1. So the next question is, okay, what's the last valid host on the 0 subnet? Well, it's the next subnet minus 2. So if the broadcast is 15.255, this last IP address is going to be 15.254. So our range of valid IP addresses on the 0 subnet is going to be whatever those first 2 octets are, 0.1 through whatever those first 2 octets are, 15.254, with a broadcast address of 15.255. Let's go ahead and do that same game again, and let's do it for subnet 32. And we can follow these exact steps. So on the 32 subnet, the first valid host is 32.1. The last valid host is going to be the next subnet, which is the 48 subnet minus 2. And minus 2 would be 47.254. And the broadcast would be 47.255. And then the next subnet, of course, is 48. So here's our first, here's our last, and here's our broadcast address for the subnet. For this next one, let's go ahead and use a /8. So our network is x.0.0.0. Our host bits are going to start in that second octet with a /8. And let's say we need to create 120 new subnets. So with the finger game, we get our thumb out, we start counting 2, 4, 8, 16, 32, 64, 128. I have 7 bits, or 7 fingers up, that represent that's how many bits it would take to create at least 120 new subnets. So our new mask is going to be 7 bits into that second octet, right there. So there's the dividing line. So our new mask is going to be 7 bits above and beyond the 8 bits we started with, which is 15. That new mask would be represented as 250 in dotted decimal as 255 dot and 254 for that second octet, which simply means that the mask is taking the first 7 bits of that second octet for the purpose of network address. So let's go ahead and list our subnets and the ranges. Now, we can have a whole bunch of subnets. In fact, we're going to have the ability to have up to 128 subnets. I don't want to list all 128, but let's go ahead and list like 4 or 5 of them to get the feel for it. So the first subnet is going to be subnet 0. And then our block size, because it's a 2, the next subnet is going to be 2. And then add 2 more, and add 2 more, and add 2 more, etc., etc. So that's our block size, and that's why we're adding that. And those are our subnets. So our subnets are going to be x dot, x dot, x dot, x dot, x dot, with that x being whatever it was. It could be a 10, it could be a 40, it could be a 195. Whatever it is, it's going to stay that way. Now, because this is the second octet where we're doing our custom subnetting, we still have 2 more octets of zeros, so we'll put them in as well. So there's our first 5 subnets. Subnet 0 would be our first, and then we have second, third, fourth, and fifth. We could also refer to them as subnet 2, subnet 4, subnet 6, etc. So now, let's go ahead and let's determine what the actual valid ranges are for each of these subnets. In fact, let's go ahead and just pick on subnet 2 just for a moment. And what I'd like to do is for subnet 2, let's identify the first host, the last host, and the broadcast address for subnet 2. The rules are exactly the same. We've listed our subnets. That's already done. We've got 5 of them right here. For the first host for subnet 2, it's going to be one more than the actual subnet value itself. So the first host is going to be x.2.0.1. And that's the first valid IP address on subnet 2. Now the last valid IP address is going to be the next subnet -2, and the broadcast is going to be the next subnet -1. Whichever one you want to do first, you absolutely can. So let's do the last address. That would be x.4.0.0 -2. So that would look like this: x.3.255.254. And that is the last valid IP address on subnet 2. And the broadcast address is going to look just like the last IP address, except it's going to be 1 greater than. So the broadcast address is 1 greater than the last IP address, and it happens to be 1 less than the very next subnet. Let's do one more. Let's go ahead and do it for subnet 6 right here, which is our 4th subnet. And what I would like you to do is go ahead and pause me right now. I'd like you to write out what is the first valid host for this 4th subnet, and what is the last valid host, and what is the broadcast, using the same exact process that we just went through together. So pause me right now. When you're done, unpause me, and we'll compare notes. So for this 4th subnet, which is subnet 6, the first valid IP address is going to be x.6.0.1. It's the subnet +1. The last valid host is going to be the next subnet -2. So that next subnet value is x.8. So it's going to be x.7.255.254. That in measurable terms is the next subnet -2. And our broadcast address is 1 less than the next subnet. So that would end in .255. It'd be x.7.255.255 for our broadcast. And that's it. What we've done in this video together is we've identified for an 8-bit or a 16-bit or a 24-bit mask how we would go about identifying not only the subnets, but also the valid IP addresses of hosts that could be in those subnets. Here's our action items for this video. Number 1, of course, is you need to make sure that you've participated in the exercises in this video about calculating the first valid IP address and the last valid IP address for a given subnet. Secondly, go back to the opt-out questions at the very beginning of this video just to validate that you can now correctly and comfortably answer each and every one of them. I have had a great time, and I absolutely appreciate the time that we have spent together. I hope this has been informative for you, and I'd like to thank you for viewing. Is there room for one more? Says the computer. In this video, we're going to take a look at calculating the quantity of how many valid IP addresses are available for each of our subnets. Here's the opt-out questions for this video. If you can answer all 3 of these correctly and comfortably, please join me in the next video. Otherwise, for everybody else, we're going to have a great time as we determine the exact number of hosts that can be fit into a given subnet. Let's begin. I'd like you to imagine that you and I have just finished a custom subnetting plan for this network topology. And we're pretty darn happy about it too, because here's what we did. We identified how many subnets we'd have to create. We recognized how many bits we'd have to steal from host address space to create those subnets. We identified the new subnets. We moved the mask over to represent the new mask for the entire network. And not only did we identify the subnets, we also identified the valid IP address host range within each of those subnets. Now, what we haven't yet done is we haven't identified how many hosts will fit in a given subnet. Now, I suppose we could do this. We could say, well, the first host is X and the last host is Y, and we could manually count between X and Y inclusively to figure out how many individual IP addresses are there in that subnet. But there's a much better way just to calculate raw quantity, and that process is this. Number 1, we're going to identify the number of host bits available. So in our topology, let's say we ended up with a /27 mask. And for this question, it doesn't even matter where we started. It's just a matter of where we ended. So we have a /27-bit mask. And my question is, how many host bits are available that the mask didn't take and allocate for the network address. So if you're thinking, well, Keith, let me think about this. We have a 32-bit IPv4 address. We are using 27 of those bits for the mask. That would leave exactly 5 bits available for host addressing if we're using this mask. And that is absolutely correct. So that's our first step for calculating the quantity of PCs, printers, router interfaces, switch IP addresses that may be in that subnet. That's the very first step, is to identify how many host bits we have to play with for that subnet. And here the answer is 5. The second thing we're going to do is we are going to use the finger game. And again, our fingers, our digits, are representing the actual bits. In this case, however, our fingers, our digits, are representing the 5 available host bits. So we're going to stick our thumb up in the air with that big old 2 on it, and we're going to say 2. And then we'll bring up our second digit and say 4, the third digit and say 8, the fourth digit and say 16, and that fifth, and that's our goal, by the way, that fifth digit in the air, and we'll say 32, and that, my friends, is very close, not exactly, but close to the number of hosts, valid host IP addresses in that given subnet. Now you might be saying, okay, Keith, what do you mean it's close? It's either, this is math, it either works or it doesn't work. Well, it is true that if we have 5 bits, we have 32 different combinations. However, not all of those are valid host addresses. For example, with a /27, we know that we're stealing the first, second, and third bits out of that 4th octet. So right here is the 24-bit boundary. There's 25, 26, 27. So here's our new boundary line, if you will, between the network and host bits. Network on the left of the blue line, host bits on the right. So here's our 5 host bits right here that the mask didn't take. So for a /27, if we wanted to know the subnets, here's the block size right there, 32. We know the subnets are 0, 32, 64, 96, and so forth. And the first 3 numbers we really don't care about because they are going to be the same on every single one of our subnets. It's this last octet where we're slicing and dicing. And the new mask, of course, would be /27 for each of those. So let's pick an example here. Let's say that this subnet 2 is going to be subnet 64. So this subnet right there. So what is the first valid host? Well, Keith, the first valid host is the subnet, as we learned in our course, and it's the subnet plus 1 more. So the first valid host would be 65. Excellent. So that's the first valid host. What's the last valid host? Well, the last valid host, as we've learned, is the next subnet minus 2. So if the next subnet is 96, the last valid host on this 64 subnet would be 94. And that is our range. And the broadcast address, I'll put B for broadcast right here, would be 95. So the reason I point that out is that this 32 is all the possible combinations we can get with 5 bits. However, we cannot, I repeat, we cannot assign the actual subnet address to a host interface like a router interface or a printer or a PC. It won't allow it. It'll say, hey, this is the actual subnet. There's no bits that are on in the host portion. It's sort of like me saying I live on like 123 Elm Street, and you ask me for my address. It'd be like saying I live on Elm Street. Well, what host or what house are you on Elm Street? No, I just live on Elm Street. It's not enough information. We have to have at least 1 bit of the host portion that is on for it to be a valid IP address that we can assign to an interface. So what that means is we have 32 minus 1 for the subnet, which we cannot assign to an individual interface. And the other one that we cannot assign to an interface is the broadcast address for that same subnet. So we're also going to do minus 1 based on the broadcast address. And for that reason, when we calculate the number of hosts available on a subnet, we're going to play the finger game, but when we get our result, we're going to go ahead and subtract 2. And that's because we cannot use the subnet itself, that subnet address, nor the broadcast as a valid IP address on an interface. So I'd like to do one more example with you on that. And that example is this. Let's say we have a /30. So we have a /30 mask. My question for you is, how many valid hosts could we put on a subnet that had a /30? Now at this point, I want you to go through this process. I'd also like you to take a moment right now and pause the screen and write down these 3 steps regarding how to exactly calculate the quantity of hosts on a subnet. So go ahead and pause me, write these 3 steps down, do the math for a /30, and then resume me and we'll compare notes. All right, how'd you do? Well, our first step on this is to count the number of host bits available. Well, 30 bits are being used for the network. That leaves only 2 bits for host addressing. So the answer to that is 2. We're going to use the finger game with our digits representing host bits. So we'll put 2 fingers up in the air and we count verbally to 4. That's our result. And then we subtract 2 because we can't use the actual subnet or broadcast address on an actual interface. So -2 equals a total of 2 possible IP addresses for valid hosts on a /30 network. So you've got it, my friend. That's exactly how we can calculate the total number of hosts that will fit as far as valid IP host addresses on a subnetwork. Our exercises for this video are simple as to make sure that you have practiced along with me in this video regarding calculating the actual number of hosts that would fit on a given subnet based on the mask. And secondly, go ahead and take a moment and check out the opt-out questions at the beginning of this video just to make sure that you are now comfortable and capable of answering those questions. I've had a great time. I appreciate you joining me. I hope this has been informative for you, and I'd like to thank you for viewing. In this video, we're going to learn how to reverse engineer a subnet based on a computer's host IP address. Here's our opt-out questions for this video. If you know the answers to these questions and are comfortable with them, I'll see you, my friend, in our next video. For everybody else, oh, you are in for a treat. We are going to take a look at how to look at an IPv4 address on a host and reverse engineer out of that to determine what the actual subnet is that that host is connected to. Let's begin. I'd like to start off this nugget by taking a look at a router interface. Let's do a show run for interface gig 1/0 on this Cisco iOS router. And here's the IP address currently configured on that interface. It's 42.255.74.251, and the mask says that the first 8, 16, and that goes out to the first 22 bits are all being used for network addressing. So that's 8 bits there, plus 8 more, and 6 bits. So 252, the binary representation of that would be 1, 2, 3, 4, 5, 6, 0, 0. And there's our dividing line. So the last 2 bits of this octet and the final octet as well, which is all zeros, are all available for host bits. So the question I have for you, and the reason I brought you here is, what if we're given an IP address like this, that's sitting on some subnet, and we are asked to reverse engineer it? So what we get to do in this video is take a look at how we can, in measurable terms, take an IP address like this and determine from that IP address what the actual subnet is that this client is sitting on. Let's bring that IP address back here. It was 42.255.74.251, and it had a /22 bit mask. So as we look at where we're slicing and dicing, we know that the first 2 octets for sure are all the network address, and we have 6 bits into this 3rd octet. So the mask would look like this: 1, 2, 3, 4, 5, 6. There's our dividing line, and these last 2 bits of the mask would be zeros. And just to be sure, we could double check. So we have 16 up to right here, then we have 17, 18, 19, 20, 21, 22. And that is correct. Also, the mask value showed 252, which is another reinforcer that we've got the mask correct. Alright, so how do we reverse engineer this? It's really straightforward. What I'd like you to do right now is I'd like you to write out these steps on paper, or if you want to do it on a computer, that's fine too. But pause me right now, write out these steps. Once you have that written down, go ahead then and resume me, and we'll walk through that process and practice it a few times. Excellent. So here's our process. Item number 1. Identify the block size. We know how to do that. We're looking at the least significant bit of the mask. It happens to be right there. The block size is a block size of 4. Now what we could do is we could say, okay, the block size is 4. Our subnets are 0, 4, 8, 12, 16, 20, etc. But check it out. We are going to have to list a whole bunch of subnets before we're even going to come close to where this host is in that 3rd octet. So instead of having to write out the, dozens and dozens of subnets to get to the range we're looking for, what we're going to do is we're going to go to step number 2, which is a shortcut. What we are going to do is we are going to divide the last network octet by the block size. What I mean by this last network octet is the octet in the IP address where we're slicing and dicing, where that mask is ending. So in the 74, what we're going to do is we're going to take 74 and we're going to divide it by the block size. So our block size is 4. It's simply this, 4 into 74, just like that. So the block size into that octet. And then we just do the math. So 4 goes into 7 one time. There's a remainder of 3. We bring down the 4. 4 goes into 34 8 times. So 4 times 8 is 32. So we bring that down. We have a little bit of a remainder, and the decimal point would go right there. And here's the cool thing. I don't care, and we don't care what that remainder is. All we were really after is how many times does this block size go into that octet? The answer, my friend, is 18 times. Right there. That's the winner. And that's step number 2. Now, step number 3, all we have to do is take that result of 18 and multiply it by the block size. And what that's going to give us, that, my friend, is going to give us the subnet that this customer is sitting on. So let's do it. 18 times 4, I'll do it longhand here. So 8 times 4 is 32. 4 times 1 is 4, plus 3 more is 7. That, my friends, is the subnet that this customer is sitting on. And now all we have to do, step number 4, is write it out. So I'll write it out in blue over here. The first 2 octets are 42.255. Those aren't going to change. But for the third octet, the actual value of the subnet is 72. And then everything after that is going to be zeroed out. So if we were working in the second octet, it'd be the same concept. Everything to the right is going to be zeroed out. And the mask we're going to put on here is 22. So we could say, in measurable terms, that the host that has this IP address, 42.255.74.251/22, is on the 72 network. Because it's literally true. Now let's take it one step further. What if we wanted to identify what the valid IP address range is for the 72 subnet? How would we do that? Now if you're saying, oh wait, Keith, I got it. We'd do it just the way we did earlier in this course. We're simply going to identify these subnets. So this is the 72 subnet. The block size hasn't changed, it's 4. That means our next subnet is going to be 4 more, and that's going to be 76. And the one after that is going to be 80, and so forth. So to calculate the range for the 72 network, the first valid host, I'll put F right here for first, is going to be x.x.72.1. The last valid host on this 72 subnet is going to be the next subnet value minus 2. So to do that, when we're in this third octet, it's going to be x.x.75.254. That's the last valid host. And the broadcast address for that 72 subnet is going to be x.x.75.255, which is one below the next subnet. And then we're off to the next subnet, which is subnet 76. So that's the process. Now, another really cool way that we could verify that that really is the 72 network that the customer is on, or in this case, the router is on, let's bring back the router for a moment, and we'll do a show IP route. If we look at the routing table for this router, it knows exactly which network it's connected to from a routing perspective, and sure enough, it's 42.255.72.0/22. And the little secret here is that the router figured that out like light years before we ever did. But as humans, we definitely have the ability to reverse engineer the IP address and determine what that actual subnet is that the customer is sitting on based on their IP address. So let's have some fun with another one. Let's say we go up to, for example, a Windows machine and we run ipconfig. We see that the IP address is 99.0.85.1/23. And that mask would be represented in dotted decimal as 255.255.254, representing that the dividing line is right here, and that we're using the first 23 bits of this customer's IP address as the network, and all the rest, which would be 9 bits left over, are host addresses. But I digress. What we want to do here is identify for this computer, this Windows machine, what subnet is it on. And what we're going to do is we're going to go through these 4 steps, And what I'd like you to do is identify what is the network segment, the subnet specifically, that this computer is connected to. So pause me right now, do that work, and when you're ready, unpause me, and we'll compare notes. All right, here's how I would solve this. I'd say, well, let's take a look first of all at the mask. What's our block size? /23, and here's how I would logically think through it. I know that the first 16 bits are all taken by, the first two octets, and then I have 17, 18, 19, 20, 21, 22, 23. Just to confirm, the least significant bit of the mask and the block size, which is 2, is our block size. The next step is to divide the last network octet by the block size. So our octet that we're dealing with is right here, 85. We divide 2 into 85, and that is 4 right there with no remainder. And then we have a 5 that goes in 2 times. That's a 4. And we do not care about anything after the decimal point. So 42 is our number, and now the third step is to multiply this result of 42 by the block size. So 42 times 2, 2 times 2 is 4, 4 times 2 is 8, 84. And so what we have here is the 84 subnet. If we brought it all down, it would be 99.0.84.0/23. That, my friends, is the subnet that this computer is connected to. Or at least it's the subnet that this computer believes it is connected to, based on its IP address and its mask. And let's do one more. Let's do a 192.168.15.19. And we'll say it's a /24. And what I want to point out with this exercise is that all of these techniques that I've been sharing with you about quote-unquote custom subnetting, they also apply even if you're using a default mask. And when I talk about default masks, I'm talking about Class A addresses by default have a /8. Class Bs have a /16. Class Cs by default have a 24. So in this example, this is a Class C address with a default mask. However, all these concepts that apply to subnetting also apply to major networks as well that haven't been subnetted, like this one right here. So if we want to know what network this computer is on, so this is an IP address on a computer, we'd first of all identify the block size. That's task number 1. Well, if with a /24, the block size, 1, 2, 3, 4, 5, 6, 7, 8, that's the least significant bit of our mask right there. Our block size is 1. So step number 2, we're going to divide this last octet where the network is, which is this guy right here. We're going to divide it by 1. So 1 goes into 15 how many times? Keith, that's 15 times. Great, then 15 times 1 is what? 15. Guess what? This guy is on the 15 subnet, 192.168.15.0/24. And when we're on clean boundaries like that, it's really, really simple. And you can just look at it and say, oh, the first 3 octets are the network, the last octet is the host address. And we really don't need to go ahead and break it down within an octet because we're on nice, clean octet boundaries for the mask. But I wanted to show you that the process still works. And that may be important just in the heat of battle. You might be given an IP address, you're not sure exactly what to do with it. You can follow the same exact process and every single time cleanly and correctly identify what subnet a given host is sitting on. Another time that this can come in handy is, let's say we're given an address like 23.40.0.0/13. And we're not sure whether or not it's a valid host address. Again, a host address has to have at least 1 bit on in its host address portion. So if we're not sure by looking at an IP address like this whether or not this is a valid host address or not, we could run through the same process. It works every time. So for example, 1, identify the block size. Well, with the /13, we have 8, and then we have 9, 10, 11, 12, 13. There's our dividing line. There's our block size. It's 8. And then step 2, divide the actual last octet where this network address lives and divide it by the block size. So 8 goes into 40, and that goes in 5 times exactly. There is no remainder. But then if we go to step 3 and we say 8 times 5, in fact, the fact that there's no remainder implies that this is a network address. But we'll finish the process. 8 times 5 equals 40. This guy, 23.40.0.0, is a subnet. We would not be able to assign that IP address to a host because it is the subnetwork address. The router or device we're trying to configure would complain it's not a valid host address because there are no bits in the host portion which are on. Our action items for this video are really simple. Number one, make sure you've done the expert exercises with me in this video, which includes specifically going through the 4-step process for extracting the subnet based on a customer's IP address. The other thing I'd have us do is go back to the beginning of this video, take a look at the opt-out questions, and make sure that now that you've gone through this content, you now have the ability to correctly answer those opt-out questions. I have had a great time. I appreciate you joining me. I hope this has been informative for you, and I'd like to thank you for viewing. Summarizing IPv4 networks. This is a great skill. You're going to love this. Here are the opt-out questions for this video, and there's 2 ways to use these. Number one, read them right now, and if you know the answer, you can safely and comfortably join me in the next video. Secondly, if you're watching this video with me at the very end, after you've learned how to do summarization, you can come back to these opt-out questions to validate your newfound knowledge. Let's begin. I've got a question for you. Why in the world would we waste any time at all learning to summarize networks if we didn't need it? The reality is we absolutely need to do this, and it happens all the time. One example might be this. Let's say this is our company or branch office of your and my company, and we have some subnets. So it's the 1771, and then we have subnet 244, 246, 248, 250, 252, and 254. And you might say, hey, those are all incrementing by 2. And that would be because the mask of 23 has a block size of 2. And indeed it does. So let's say this branch of our company is connected to the internet, and we have a virtual private network over the internet connecting to our headquarters office. Now my question is, how many routes are we going to have on our corporate router here to reach the 244 and the 246 and the 248, etc. networks? Well, the first answer might be, well, we need 1, 2, 3, 4, 5, 6 routes. And we could easily do that. We could either dynamically learn 6 routes, or we could statically configure the 6 routes that go over this VPN. And with 6 routes or 6 networks, it's not a huge deal. However, think about this. What if we had 100 branch offices, and each of those branch offices had dozens and dozens of networks? Now we're taking a look at thousands and thousands of routes. If one of these networks has a problem or goes up or down, the routing table at our headquarters office is also going to reflect that. Using summarization buys us 2 things. Number one, we could have a summary route that says, hey, dear Mr. Headquarters Router, to get to all these guys, here's a single route to go ahead and use to reach all of those subnetworks. That's great. And secondly, because the headquarters router doesn't have to know the details of the 244 subnet or 246 subnet, if one of those networks goes down or has a problem, it's not changing the routing table on this headquarters router, which is already pretty busy already. So that is just one of many benefits of using summarization. We're also going to be using summarization techniques as we take a look at wildcard masks in access lists, as well as network statements in routing protocols such as EIGRP and OSPF. Now here's the million-dollar question. What is that magical summary route that can summarize all of these networks? So here's my question for you about summarization. Do all of these subnets under the 1771X, with X being the actual subnets, could we summarize those by using something like this, 17.0.0.0/8? Now, you and I both know what that 8 means. It means the first 8 bits are being used for the network, and the last 24 bits are not being used for the network address. So if we look at this network over here, do all of these subnets, do they all begin with 17? And the answer is, holy shnikers, they do. They all start with 17. So 17.0.0.0/8 would be a summary of all of these networks. Now, I'd like to share with you the problem of using this summary. What if we have another branch office that's using 17.42.x.0/23? This summary of 17 anything not only covers this whole area of our network, it also covers a network that's using 17.42. It also covers any networks that's using 17.49 or anything else that begins with 17. What this right here is an example of is a gross over summarization. In fact, do you want to see what the ultimate summarization is? It looks like this. You may recognize it. And that's what a default route looks like on a lot of routing devices. It effectively says the mask is a /0, which means everything matches. A default route is like the ultimate summarization because it covers the entire range of IPv4 addresses. That's why in a routing table, we have more specific routes that are used first. And if a router can't find a more specific route, the default route matches. Because it's effectively saying, I don't care what the address is, this is going to be a match with a /0 mask. So getting back to our point, we don't want to use a incorrect summarization that's summarizing additional networks above and beyond what we intended. I remember a movie back from the 80s called Top Gun. And in there's a quote that goes something like, "Son, your ego's writing checks your body can't cash." Well, in the case of a incorrect or a gross over summarization, this summary is representing more, a whole bunch more, than just the subnetworks in a certain part of our network that we intended. So here's the process that you and I get to use to create an accurate summary for a set of subnetworks. It's these 4 steps right here. I'm going to walk you through them, and then I'm going to have you write out the steps, and then we'll do some exercises to practice those steps together. Our first step is to find the common ground between all of these subnets. So how many bits, starting from the left, in the IP address of those subnets, how many are common? And our address is 1771X, with X being that actual subnet. So here's what I can tell you, just by looking at this, because we have a /23 mask, the first 2 octets are going to be identical for all of those. So we know that the first 16 bits are all the same for each of these subnets. For example, it's going to be 1771 for subnet 244, 1771 for subnet 246, and all the way across the board. So we really don't need to slice and dice and dissect those 2 octets because we know that all subnets are using those same 2 octets that are identical, and that's the first 16 bits. And now we come down to the actual subnet value here in this 3rd octet. So we're going to use our table up here for our 3rd octet, and let's go ahead and identify out of the 3rd octet what the common bits are. So our subnets are 244 and 246 and subnet 248 and subnet 250 and subnet 252 and subnet 254. Make sure I got all of them. So there's 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5, 6. Okay, that's the 6 subnets that we want to create the summary for. And we know the first 2 octets are going to be 1771. Now what we need to do is find out from that 3rd octet how many of the bits out of all those addresses are exactly the same. Now here's my question. How in the world do we convert this decimal number of 244 and 246 and so forth into binary? Now, if you're saying at this moment, "Oh, nuts, I should have watched that video called Beautiful Binary and Binary to Decimal Conversion," because that's where those concepts were covered, I would strongly encourage you to pause this right now and go take a look at those videos. They will benefit you. If you've already been through those videos, you might be saying, "Oh, Keith, I got this." We're going to play the game called Does This Go Into? So we'll start with 128 and say, does that go into 244? And the answer is, for this guy, yes it does. For 246, yes, 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 and yes. And then we're going to subtract 128 from each of those. So if we were going to do this longhand, which I'm going to do with you this first time, we go something like this. 244 minus 128, 246 minus 128. For this one, the remainder is 116. And all the other numbers were 2 higher than the previous, so the remainder is going to be 118, 120, 122, 124, and 126. And then we keep playing the game. Then we take the number of 64 and say, does that go into each one? And the answer is yes, it does. It goes into each of those results. So we have minus 64, minus 64, minus 64. Now, after a while, you may be able to shortcut this a little bit, but for now, I would make sure that you know how to do it the long way. So the result of each of these would be 52 for this one, 54, 56, 58. And then we play the game again. So we got to say, now does 32 go into each of those? And you know what? It absolutely does. So we have a 1 in each of those positions, and we minus 32 from that. And with your permission, I'd like to bring my results up here because I'm out of room down here. So 52 minus 32 is 20. The next one's going to be 2 higher, 22, 24, 26, 28, and 30. And then we continue playing the game. Okay, does 16 go into each of those? And the answer is yes, it does. Minus 16, 16, 16, 16, 16, 16. It does go into each one of those, so we put a bit on in that position as well. And then we get our remainders. So the remainder here is 4, and then we have 6 and 8 and 10 and 12 and 14. And then we continue playing the game. So the next question is, does 8 go into 4? And the answer is, no, it doesn't. So let's just do this column real quick. Does 8 go into 6 for the second network? The answer is, no, it doesn't. Does 8 go into 8? And the answer is, yes, it does. It goes in one time, so there's a minus 8 right there. And also 8 goes into 10, so minus 8 for a result of 2. And the next one and the next one, so we have minus 8, and we have 4 and 6 as results. Now as we move down to this next number of 4, it goes into this first one time, and that's minus 4, and he is out of the game, so it's 0, 0 for the rest of his bits in that octet. The 4 also goes into the 6, so we'll put minus 4 here, the remainder is 2. And so we'll go ahead and put his 2 right there to finish him out. And then for this third subnet, he is done. He has no remainder there, so we're going to 0 that guy out. The next subnet, we have a 2 left, so that 2 goes right there. Everything else is 0'd out. The next subnet has a 4 left over, so we know that the 4 goes in one time, everything else is 0'd out. Again, it's like an accounting game. We're getting down to 0. And then for 6 here, we're going to have a 1, which is minus 4, a 2 left, and then we have a 2, which is minus 2, and we're at 0 there as well. So there's the binary equivalent of each of those. If you'd like to brush up on your practice for conversion of decimal to binary, the 2 videos I'd recommend you watch, again, are Beautiful Binary in this course and the binary to decimal conversion video. Between those 2 videos, it has all the details regarding what we're reviewing as far as the conversion process that we're doing right here. So that was step number 1, finding the common bits. And I'll walk you through another scenario here in just a moment, and I'll show you a little shortcut to this process. But I want to make sure that you had the details behind the scenes of what's really happening. So we found the common bits. And the common bits, if we look from left to right, the common bits between all of these 6 networks is right there. Because if we go any further to the right, they start to not be the same as each other. And all we're going to do is we are going to go ahead and use that as our new mask boundary. So our mask is going to go all the way up to these first 4 bits. And then step 3 says we're going to go ahead and 0 out everything to the right. Just pretend it doesn't even exist for the purpose of our summary address that we're creating. And then indicate that new summary and the mask. So the new summary would be 17.71. Those first 2 octets have not changed. We take the value of these 4 common bits out of each of the subnets, and it would be 128 plus 64 plus 32 plus 16. The sum of those 4 higher order bits are 240, so it would be 240.0. We 0 out everything to the right, and that new mask would be how many bits? How many bits from left to right for the entire IP address are we now representing as a network address? And the answer is we have 8 here and 8 here, which is 16. Plus, we have 4 more, which would be 17, 18, 19, 20. So our new mask would be a /20. So 17.71.240.0/20 is a summary address that closely represents these 6 subnets. So what I'd like you to do is I'd like you to write out these steps 1, 2, 3, and 4. Take a moment, pause, write out those steps, and then we're going to do another exercise together, and I'm going to change the subnet numbers so we aren't working with the exact same numbers as we were previously. Pause me now. When you've got them written down, go ahead and click on Resume. So let's mix it up a little bit. We'll still use a /23-bit mask, but for our subnets, let's go ahead and use subnet. Let's use 52 for here, and 54, and 56, 58. Down here we'll have 60, and over here we'll have 62. So our objective is to create one summary for all these 6 networks. So the first step is to find the common bits. Up here for these subnets, we have 52, and 54, and 56, and 58, and 60, and 62. If we play the does it go into game, we know that 128 doesn't go into any of those numbers. And if we want to just do one network at a time, for example, this octet of 52, we know there's no 64s. There's a 32 in there, which has 20 left over. So out of that 20 left over, we have a 16. Then there's 4 left over. We have a 4, and all the rest are zeros. By practicing the decimal to binary conversion, you'll get faster and faster at doing it without having to write it out longhand. And for these others, which I know are just 2 more, I can just go ahead and use the same numbers up to that point and add the 2. So that is 2 more than the previous one. And then for 56, I need to add 2 more here. So I'm going to 0, 1, 1. And it gets a little bit tricky when you're adding in binary, because if we add 1 to this position, those 2 roll over. So it would actually look like this, 1, 0, 0, 0. And this next one is 2 more. And this next one is 2 more than the previous one. So again, we're adding a 1 here. Because it's binary, there's only 2 positions, we are going to carry the 1. It's going to look like that. And for 62, it's going to be 2 more. So it's going to be 0, 1, 1, 1, 1, 1, 0. And if you want to do it longhand and just verify your work, that's perfectly fine. There's no harm in that at all. But the reality is we do have to find out what the binary is so we can draw the line regarding the common bits. And just to double check our work, if we wanted to verify that 62 really is this number, we could say 32 plus 16 plus 8 plus 4 plus 2 is, and add those up. So 6 plus 2 is 8, 8 and 8 is 16, plus 4 more is 20, plus 2 is 22, so we carry the 2 up here, bring the 2 down there, and then add up the tens position. 3 plus 2 is 5, plus 1 more is 6, 62. Just to validate that we didn't get our math somewhere wrong in the process. So there's the binary representation of those 6 subnets, and all we do is we find out where the bits are in common. So the 128 bit is in common, the 64 bit's in common, the 32, the 16, and you know what? That's where the dividing line is, right there, because after that point they start not being common anymore. So that's our very first step, find the common ground, the common bits going from left to right. Second, use the mask to cover the common bits. So this new mask is going to be shorter. We are creating a summary, which means a shorter mask to summarize multiple networks or subnetworks. So the new mask is going to be the first 8 bits plus the next 8 bits, and then we are using the first 4 bits of that third octet. Now check this out. As we write this out, 17.71. What do we put for these 4 bits? You put whatever the value is of those 4 common bits, which are 0 plus 0, there's no 128s, no 64s, 32 plus 16, which is 48 right there. So that's 48, and then we zero out everything else. And the new mask is going to be 16 plus 4 more bits for the mask. So it'd be 16, 17, 18, 19, 20, and that new mask would be 20, representing the length of the common bits. So this 48 is the value of those common bits in that third octet. And that /20 is representing how many of those bits are in common. So the Reader's Digest version of this says the first 20 bits of all of these subnets are identical to each other. And that's what makes this summary address appropriate to represent these 6 subnets, because they all have the same first 20 bits. So let's do another one. So you should have these 4 steps written out so that you can go ahead and follow the process. And here's what I'd like to do. Let's go and use 95.0.0.0/11. So our block size is 32. And what I'd like to do is let's go ahead and let's create a summary for the 0 subnet, for the 32 subnet, for the 64, and the 96 subnet. So that's the first 4 subnets that we could carve out using 95.0.0.0/11. And of course, this 95 would be brought down for each of those. And here is your expert exercise right now. Using these 4 steps, I'd like you to identify a summary address for these first 4 subnets of the 95.0.0.0/11 address space. So go ahead and pause me right now, do that exercise, and when you're done, click on play, and you and I will compare notes of exactly what we came up with. Here's how I would approach this. The first step is to go ahead and say, well, what are the common bits between these 4 subnets? And we have to calculate what the binary values are. So for 0 subnet, 32, 64, and 96, we can basically say, well, 0 is all zeros. That was pretty straightforward and easy. 32 has 132 and the rest are zeros. 64 has a 64 and all the rest are zeros. And 96 has a 64 and a 32. And the more you do this math and practice with those conversions, the faster you will become. So out of all these bits going from left to right, which bits are in common? Well, it looks like just this column right here, the 128th position, and then after that, they've all got different values. So our new mask is going to be drawn right here. So just as a reminder, the original mask, 95.000/11, the original mask is here, this blue line, and our new summary is going to be this green line. So this second step is we are now going to use a mask to identify what those common bits are. So the first octet of 95 is common to all 4 subnets, and this very first bit of the second octet is also common. So our new mask is going to be a /9. This is the new mask for the summary. Whenever we're doing summarization, the mask is going to be shorter to summarize a larger quantity of networks that are being summarized beneath that. The third step is to go ahead and zero out the rest. So in this case, the first octet is going to be 95. We then represent whatever the value is of this 128 position, which happens to be 0, and then everything to the right of that gets zeroed out as well. So our summary address is going to be 95.0 because we had nothing on in those common bits between the 4 subnets, so we don't put any value there, and then we zero out everything to the right and put the new mask on, a /9. And that's step number 4. Indicate the new summary and the mask. So 95.000/9 is a summary of those 4 subnets. And I also want to point out that if we had said 10 accidentally and said the line's right here after the 64-bit, these bits in this 64 position aren't the same. It wouldn't correctly summarize those 4 networks because these bits in this 64 position are not the same between all 4 networks. So let's do another one with the 33.33 network, .0.0/, and let's go ahead and use a 22. And let's summarize a few of the subnets in that range. Let's go ahead and summarize subnet 44. Again, this third octet is where we're going to be looking. And 48, and 52, and 56. So what I'd like you to do right now, using this 4-step process, go ahead and pause me, work through the process as we've done previously, figure out what the correct summary address is for just those 4 subnets, and then resume me and we'll compare notes. Alright, step number 1, find the common ground, the common bits in that third octet. Because we already know that the first 2 octets are all exactly the same for all those subnets. So we're really just slicing and dicing this third octet. So we have 44, and 48, and 52, and 56. So for 44, we know, first of all, we know that 128 doesn't go into that, and 64 doesn't go into 44, but 32 does. So 44 minus 32 has a remainder of 12. So 16 does not go into 12, but 8 does, and 12 minus 8 is 4. So 4 goes in, and then we have nothing left over. So that's 44. Do the same thing for 48. 128 doesn't go in, 64 doesn't go in, 32 does go in. That has a remainder of 16, and that makes 16 go in one time, and we are out. So there's no more value left, so we're going to put zeros. Then we take 52. Now I know 52 is 4 more than 48, so we're going to add a bit here, and all the other bits are going to be the same because it's 4 higher, and 56 is 4 higher as well. So it's going to be 0, 0, 1, 1. We have to carry the 1. That's going to be a 0, 0, 0. And you may just want to spot check 1 or 2 just to make sure that you've got the conversion correct. So in the case of 56, if we just want to spot check, we have 32 plus 16, which is 48, plus 8 more, equals 56, and all the rest would be zeros because that's perfect. So the next step is to use the mask to cover the common bits. So if we go from left to right, how many of these bits are common? And I'm seeing all the way up to this point right here, because beyond this point, they're not common. So we already have 16 bits in common for the first 2 octets, and the first 3 bits of that third octet are also in common. So the mask for our summary is going to be 19, which is 16 representing the first 2 octets, which are going to be identical, and the first 3 bits of the third octet, which are also identical. So our new mask is /19. That's step number 2. We're going to not worry about the rest of these bits because the mask only goes up to this point. That's step number 3. And then we're going to indicate the new summary along with the mask. So the new summary is going to be 33.33. these first two octets, which are identical, and then whatever the value is of these three common bits that are the same for all these subnets. So because there's 001, we have no 128s, no 64s, we have a 32, and that is the value of that third octet. And then after that, we zero out everything to the end of the IP address. So the summary address that identifies these four subnets is 33.33.32.0/19. Now I do have an observation that I want to share with you, and that is this summary isn't only for these four networks. We also are very likely going to capture any other subnets that have these high 3-order bits in common. For example, if we had 33.33.40.0/22 as one of our subnets, in fact it's the subnet before this guy right here, would that be included as part of our summary? And if we take a look at 40, I'll put it in green as well. If we have 40 right here, it's going to be 0, 0, 1, that's 32, plus 8 more, which would be 0, 1, and then these would be zeroed out. And check it out. Because its 3 high-order bits right there are also 001, this summary address also would include the 40 subnetwork. So at the end of the day, this summary address that we created is a good summary for these four networks. It's not watertight, but it's very, very close. And as network designers build IP addressing schemes, what they're going to do is strategically place groups of IP addresses and subnets in various parts of the network so that when it does come to summarization, they can get very nice and clean summarization boundaries that won't over-summarize any additional networks. But to do that, it never happens by accident. It's only through planning. Our action items for this video are simple. Number 1, make sure you've done the expert exercises together with me in this video so you can correctly create a summary address for a group of subnetworks. And secondly, I'd like you to take just a moment and review the opt-out questions at the beginning of this video. Now, the reason for that is because once we've gone through this together, it'll help reinforce the concepts we've learned, and secondly, it will help validate that you currently can create a summary address given a set of IP subnetworks. I hope this has been informative for you, and I'd like to thank you for viewing. Wild card. Dun, 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 dun. Oh, that's wild thing, not wild card. Well, in this video, you and I get to take a look at this wild card mask and how it applies to Cisco iOS access control lists and network statements. Here are the opt-out questions for this video. And what I've noticed is that a lot of times people will go through this multiple times. And the great thing is every time you go through, if you get to the opt-out questions and you realize what the answers are and why, you can save time and just go to the next video. For everybody else, however, or if you want to do a review of the content, let's jump in. Cisco has lots of different operating systems, and one of those is called the iOS, the Internetwork Operating System. And inside of iOS, we can do lots of things like configure the router, configure IP addresses. One of the things we could do is create access control lists that identify certain traffic on the network. And access control lists are used for all types of things. We could use them as part of IPsec configurations for identifying interesting traffic. We could apply access control lists as filters at interfaces. We can use them for quality of service. The list goes on and on. In short, an access control list identifies traffic. Another function that we can use inside of iOS is a network statement inside of like OSPF or EIGRP that's going to include or specify which directly connected networks are going to participate in that routing protocol. Now, to be clear, if you want a full discussion on access control lists and network statements and how they work, I would strongly encourage you to check out ICND1 from Jeremy Char right here at CBT Nuggets. Our purpose in this nugget, however, is to identify how a wildcard mask plays in to those types of mechanisms when we're dealing with IPv4 addresses. Now, it's true that every human on the planet deserves to be loved and cared about. However, in IPv4 addresses, we may or may not care about all of the bits in an IP address. For example, let's say that you and I are the administrator and we're going to create an access control list and we want to identify any traffic that is coming from the network 142.13.0.0/24. So effectively, the bits that we care about is we want to go ahead and match anything in the first 3 octets, but we don't really care about that last octet. Why is that? Because if we want to get the entire subnet, we want to match on anybody from that subnet, the actual last octet could be anywhere between 1 and 254, the valid IP addresses for that subnet. So inside of an access control list, how do we indicate that we care about matching on the first 3 octets and don't care about the actual last octet? It could be a wildcard, if you will. And the answer is we use a wildcard mask. So inside of an access control list, using all the proper Cisco iOS syntax, we'd spell out the network that we want to match of 142.13.0.0. And what we're going to do for the wildcard mask is we are going to put the bits on for the bits that we do not care about matching. So in this case, if we want to match on the 142, we put a 0 in this wildcard mask, which we are now drawing. So the first octet, the wildcard mask says, I care. I care about matching on all 8 bits. It has to be 142, or the binary equivalent. The next octet we also care about, so we put a 0 there, which means to the router that we have to match on all 8 bits of that second octet, which are in decimal 13, and whatever the binary equivalent of that is. If we care about matching on the third octet, we'd also go ahead and put a 0 in the wildcard mask in that corresponding position. And then for the very last octet, this guy right here, where we don't care what the value is, we simply turn all the bits on because we don't care about those bits. And so the last octet would be 8 bits on, which in decimal would look like this, 255. So when we have nice and even clean boundaries between octets, like we have right here, here's the network, all we're really doing is we are inverting the mask. Because the mask for this network would be 255.255.255.0. And check out this wildcard mask. It's just flipped. Where there was a 255, there's now a 0. And where there was a 0, there's now a 255. So on networks where there's a nice clean break right in the middle between 2 different octets, all we do is simply invert the mask. And that's how we can create wildcard masks, is simply by inverting the subnet mask, and poof, you've got a wildcard mask. It's also important to note that wildcard masks, they do not have to be contiguous. So if you're at the CCIE level and out of the second octet, you want to look for just odd networks or just even networks, you could actually flip some bits in the wildcard mask anywhere you want to. It just means that anywhere you do, you don't care about that corresponding bit. But for the average person, you're not going to get into discontiguous wildcard mask bits. So let's do one more. Let's say we have a network of 25.0.0.0/8, and that's what we want to match on. And in an access list, an extended access list inside of Cisco, you can match on the source address or destination address. So if we want to match on the 25 network, and the mask would be the normal mask, 255.0.0.0, which is a dotted decimal way of saying it's a /8. So if we were going to create a wildcard mask for this that says, hey, we care about matching on the first octet, but we don't care about the last 3 octets, we'd simply flip this mask. So the inverted mask would be a 0 for the first position, and the last 3 octets, because they're currently 0s, would go to 255.255.255. Just like that. Again, if we have nice clean boundaries, it's super easy to do. And let's do one more. Let's say we have a 172.16.0.0/16. The mask for that in dotted decimal would be 255.255.0.0. And the wildcard mask that we would use inside of an access list as an example would be 0.0.255.255. We're simply inverting the mask on even boundaries. And that's step number 1. The simple and easy guide to creating wildcard masks. Now the tricky part is, what if we have a subnet or a summary address like this, 42.13.64.0/19? If you'll notice, that 19 is not a clean boundary. The clean boundaries are 8, 16, and 24. Anything other than that is not a clean boundary. So how in the world do we calculate what the wildcard mask is for this subnet? Or it could be for this summary, which could be a summary of multiple networks. So here's one approach to solving it when we don't have a clean boundary to play with. And that is, we're going to take the least significant bit of the mask and then -1. So if we look at the mask, it's 19. So we have 16, then we have 17, 18, 19. There's our dividing line right there. There's our block size, which is also the value of that least significant bit. And we'll simply -1. So our wildcard mask would be 0 for here, so that was 255, that gets flipped. It was 255 here, that gets flipped. And for this octet where we're slicing and dicing, we simply take the least significant bit of the mask, also known as the block size, and subtract 1 from it. So it'd be 31 right here. And then for this last one, because we don't care about any of those bits in the very last octet, those host bits, it'd be 255, just like that. I kind of like that method the best because we already know what the block size is. You simply subtract 1, and that's going to be your wildcard mask. Another way of doing it, if you want to, you could go ahead and put 255.255.255.255 on the first row, and on the bottom row you could put the mask for the actual subnet. So the mask down here is going to be 255.255, and then for the /19, the mask is 224 right there, .0. So you just put all 255s on the top, you put the normal mask next, and you simply subtract the mask from the top row. So 255 minus 255 is 0. Same thing here. And 255 minus 224 is magically 31. And then 255 minus 0 is 255. So what I'd like you to do right now as the first expert exercise is I'd like you to write down the 2 steps. And that step number 1 is that if you are on even boundaries, you can just invert the mask. If it was a 0, it's going to be 255. If it was a 255, it's going to be a 0 in that same position. And the second step is that if you are subdividing an octet, you simply take the least significant bit value of the mask and subtract 1, and that's going to be your wildcard for that octet. If you want to play with the third option right here, that's fine too. But it's going to be a lot faster, at least it is for me, if I take the block size of the current network minus 1. So go ahead and pause me now, write down those steps, and then when you're ready, hit play, and we'll do a couple more together. I'd like to point out something, is that this table over here, you'll notice that we've been using it almost every single video. So if I was working, for example, manually through some IP subnetting, I didn't have a subnet calculator handy or what have you, I may not write out this part of it, and I may not write out these mask values because I know them just from using them quite frequently. But I definitely would write out these weights and use them almost every time. Because when in doubt, in the heat of battle, by actually making the little notes and drawing a line, identifying where that mask is, what the block size is, that's super helpful in virtually all of these calculations. So I would encourage you as well to continue to write this out, at least this weights line for each of the positions in 8 bits of a byte of data, which in our case is 8 bits in an octet of an IP version 4 address. So here's our next expert exercise. We have an address of 99.1.3.4/30. And let's say we want to include that inside of an access control list. My question for you is, what would be the wildcard mask to match on the first 30 bits and not care about the last 2 bits? Your steps are right here, steps 1 and step 2. Go ahead and pause me right now, work it out, and when you're done, click on play, and we'll compare notes. All right, good work. So here's what I would do in going through this. I'd say that the mask to begin with is 255.255.255, and then as we go 6 bits into that last octet right there, the mask would be 252 for that very last octet. So that is the subnet mask for that subnetwork. Now to calculate the wildcard mask, which is required to actually put into the configuration if we're doing an access list, we'd go ahead and invert the full octet, so that'd be a 0, 0, 0, and that's all step 1. Invert the subnet mask on even boundaries, so 0, 0, 0. And then for this last guy, 252, we're going to take a look at the least significant bit of the mask, which in this case, our block size is 4. That is the least significant bit value. And subtract 1. So that's going to be a 3. And that is our wildcard mask right there for this subnet. And that same exact process would work whether it was a summary address or a custom subnet, because it's all based on the value of that least significant bit of the mask minus 1. So let's do one more. Let's say we have a network of 1.2.3.0/25. So there's our network statement. And what we want to do is create an access control list that's going to identify that network, 1.2.3.0/25. Step 1 is to invert the mask on even boundaries. So I'm going to draw the subnet mask manually, 255, 255, 255. dot, and that would be a 128 because that first bit from that fourth octet would be on, and that would be a 128. And then simply invert the nice clean boundaries. So that'd be 0.0.0. And for that last octet, we're simply going to take the value of the least significant bit, which is 128 in this case. That's our block size. Minus 1, which would be 127. And that is our wildcard mask. So whether we're using this wildcard mask in our network statements for OSPF and EIGRP, or we're using it in access control lists, the process for calculating that wildcard mask is the same every single time. Our action items are simple. Make sure that you've gone through the expert exercises in this video with me, and make sure you've gone back up to the opt-out questions that you should now be able to comfortably answer. I have had a great time. I appreciate you joining me. I hope this has been informative for you, and I'd like to thank you for viewing. Is it possible to start subnetting at a non-8-bit boundary? And the answer is absolutely yes. That's what this video is all about. Here are the opt-out questions for this video. And as I was writing this one right here, it occurred to me how much progress that you and I have been making throughout our journey together. And here's what I'd like to do. Once you've completed this video and you come back and look at this question, if you know the answer to it, I would like you to give yourself a huge pat on the back, and I would like to give you a huge kudo as well. And to do that, if you do me a favor, once you've come across this question and can answer it, jump over on my Keith Barker Networking fan page and just leave me a comment saying, Keith, the answer is, and then give me the answer, because I would like to say, personally, congratulations to you as well. Because that represents a lot of work, and it also means that you have some pretty darn amazing IPv4 subnetting skills. Congratulations. All right, that being said, let's jump right into doing subnetting starting on a non-octet boundary. Earlier in this course, you and I went through a video called Classes, Masks, and Private IPs. And in that video, we learned that there's a class A, B, and C address, and we learned the ranges, the very first octet, to how to identify a class A, class B, or class C. We also identified that the A, B, and C, by default, have a different mask. So for example, a network that's 10.0.0.0 by default is going to assume an 8-bit mask because it's a class A address. A class B address, for example, in the 180.20.0.0, again, that first octet is in the class B range, the default mask is going to be 16. And then for a class C, for example, 200.10.30.0/24, we're going to have a 24-bit mask by default. Now, in the production environments where we work, are we using a default mask most of the time? The answer is absolutely not. However, the reason this is important is because if we're given an IP address and we're not given any mask information, and if we were asked to do custom subnetting on these, we could go ahead and presume the default mask and start stealing bits based on that default. On a class B address, we could start stealing bits from the 17th bit. And on a class C address, we could start stealing bits from the 25th bit. But as I mentioned, we're not using a whole bunch of defaults anymore, and perhaps we're given a network address. Maybe it's already a custom subnet, and they're asking us to go ahead and further subdivide that network. And that's what I like to focus on in this video, is doing a strange beginning, a strange starting point. So even though we might be given an IP address or a subnet address to start from, the process is pretty much the same as it has been as we've done throughout this course. So let's go through an example. Let's say our boss walks up to us and says, I've got this address space 10.20.30.64/27, and what I would like you to do with it, the boss says to us, is go ahead and create 4 brand new subnets, all within this space, and please make sure that each of those new subnets can support 5 hosts each. And that's important. If we use all the IP address space for network addressing, we might end up in a situation where we have little or no host bits left for actual host addressing. So we want to make sure that each new subnet can support up to 5 hosts. Those hosts are going to include the router interface for routing traffic on and off of that subnet, and then up to 4 other IP addresses. They could be printers or other devices that would be on that subnet. So how do we go about doing something like this? The very first step is to take what you have, and we've been given this as our network to play with. And then secondly, we're going to determine the number of subnets that we need to create. So here's my question for you. How do we figure out the quantity game for subnets? How do we know how many additional bits we need to steal from host portion and allocate to subnetting to get 4 new subnets? Now, if you're saying, oh, Keith, I got it. We're going to use the finger game. And I'm going to put my thumb up and say 2. And I'm going to put my other digit up and say 4. And I'm going to stop. Because 4 is exactly how many subnets we need. And if you look at your hand, you've got 2 digits up. That represents the number of bits that we need to take. So the new mask is going to be 2 more than the old mask. So the new mask is going to be at 29. So that's step number 2, determine the number of subnets and apply the new mask. And then step number 3 says validate that there's enough host bits left over for the number of hosts needed. So let's do this. Let's imagine that this is our 4th octet. The new mask, if we have 24 here, the new mask in that 4th octet is 25, 26, 27, 28, 29. So there's our dividing line. And these last 3 bits are available for host addressing. So as a quick check, how many hosts could we fit on a subnet where there's only 3 host bits for host addressing? Now, if you're saying, hey, Keith, that's the finger game again, you're exactly right. So we're going to take those 3 bits. We're going to start off with a 2 on our thumb, bring up another digit that brings us to 4, another digit that brings us to 8, and then we're going to remember that even though we have 8 different possibilities with 3 bits, we're going to sacrifice 1 to the subnet address itself, and we're going to sacrifice another one for the broadcast. So we have to take that 8 and subtract 2 from it. But still, that gives us 6 possible hosts, so we're still in good shape. We have 6 possible hosts on each of those subnets. So then all we need to do is calculate the valid host range for those subnets. So we know that our block size right here is 8. And we also know that our very first subnet looks like the parent subnet. Remember how we did subnet 0? So it'd be 10.20.30.64/29. That's our very first subnet from this parent network. And then just looking at our block size, the next subnet is going to be 8 more. So 10.20.30. And then 64 plus 8 is going to be 72. And that's our next subnet. And the next one is going to be 8 higher than that, which is subnet 80. And our 4th subnet is going to be subnet 88. And they're all going to have a /29 mask. And they're all going to have 10.20.30 as the first 3 octets. So here's my question for you. What would the valid range of IP addresses be for these hosts? And if you're saying, Keith, I've got this too. We've learned this already in this course. The first IP address on a subnet is the subnet plus 1. So the first IP address here would be 65. And then the first subnet on the 72 network would be 73. And the first IP address on this subnet would be 81. And the first subnet on this network would be 89, just like that. The last valid host is going to be the next subnet minus 2. So this is going to be through 70. The 72 subnet is going to be through 78. The 80 subnet is going to be through 86. And this last one is going to go all the way through 94. So there's our brand new 4 subnets all fitting within this space, and there's the valid host range for each of those. Now I'd like to show you something else very interesting. In this major network, the 10.20.30.64/27, which, by the way, is a custom subnet to begin with, I'd like to ask you a question. What would be the next subnet on this network if it's a /27? We've just, by the way, used up all the space in the 64 network. What would be the next network? The easiest way to find out what the next subnet is in the big picture is to take this mask of 27 and realize that 27 goes 3 bits in, so it has a block size of 32. The next subnet is going to be 32 more. So our next subnet is going to be .96. And the next subnet after that is 32 more, which would be 128. All /27. And I want you to notice this last valid IP address right here of .94 is absolutely 2 less than the next major subnet, which is 96. All we've done is we've taken the 64 subnet and we've carved it up into smaller chunks using the same exact process we've learned earlier in this course. It's just that our beginning point for doing the custom subnetting didn't happen to fall on a nice clean octet boundary. Let's do another one, and we're going to get a little bit more wacky with the boundaries. Let's take this network of 195.3.40.0/21, and let's say that we need to create at least 12 brand new subnets And each of those subnets needs to have at least support for 100 IP addresses that can be assigned to hosts. For example, the router and printers and other PCs and Linux boxes and Macintosh that are all sitting on those new subnets. So starting with what we have a /21. We need to determine the number of subnets, which is 12, and apply a new mask. So how many bits do we have to steal to get to 12 subnets? So if we play the finger game, we have to steal 4 bits above and beyond what we're given. So if we take a look at plus 4 more bits, the new mask is going to be a /25. Now with 25 bits being used for the actual network, so if we have the first 24 bits, and then we're looking here at the 4th octet, so we're using a bit here, and then that's the dividing line. Can we support up to 100 IP addresses? And it's again the finger game. So we have 7 bits here. If we play the finger game up to 7 digits, that's 126 possible hosts. So as it turns out, we will have enough host bits available to support up to 100 valid IP addresses. In fact, up to 126, but all we need in this scenario is up to 100. So that will meet our needs. So we've got our new mask. We've validated that there's enough host bits available for host addresses. And now what we need to do is identify the networks and their ranges and put them to work. So our block size right here is 128. In this new mask, we're dealing with the 4th octet. So our first subnet would be 195.3.40.0. Remember, the first subnet is going to look identical to the parent network. It's just a different mask. And then what we get to do is we get to go ahead and add that block size for our next subnet. Again, we're in the 4th octet. So the next subnet would be 195.3.40.128/25. And that's our next subnet. Now the reason I'm using this IP addressing scheme on this example is I want to point out something that is going to happen, and you need to be prepared for it. And that is, what happens if we try to add 128 again to this last octet? It's going to be 256. An IP address octet for IP version 4 only has a valid range from 0 to 255. So what it really means when we're adding a 1 here in this 128th position, we are really going to carry over the 1, and the next subnet is going to look like this, 195.3. And because we're carrying the 1 into the next octet, it's going to be 41.0. That's our next subnet, /25. And the next subnet is we're going to add 128 again to that last octet, 195.3.41.128. And the next subnet is going to be 195.3.42.0. Again, these are all /25s. So now if we were to calculate the first valid host on these subnets, I was running out of room there, so I decided to put it up in text format. So out of our 5 subnets, here are the actual subnet values. Here's the first valid host address for each of those subnets. This is the last valid IP address on each of those subnets. And over here we have the broadcast address for each of the subnets. So just as before, if we have 41.0 as the subnet, the first valid IP address is going to be 41.1. The last valid IP address is going to be the next subnet -2. So if the next subnet is 41.128, this last IP address of the previous subnet is 126, and the broadcast address is 1 less than the next subnet, which in this case is 41.128. One of the concerns that comes up quite a bit for students is that, okay, what if I'm practicing and I'm creating all these custom subnets? How do I know my answers are correct, that I'm doing the math correctly? And one great way to validate that is to use a little assistance in the way of a subnet calculator. Here is one of many that are out there. This is at Cisco's webpage. If you just go up to the top right-hand corner and search for IP subnet calculator, it'll ask you to log in. A login at Cisco Connection Online is free. You can then go ahead and start using the tools. For example, in the IP subnet calculator, let's go to subnets. And let's say, for example, that we started with a network of 36.25.0.0, and we are stating that we're going to use a 16-bit mask. See, the cool thing is right here, it's showing us the dotted decimal format and the prefix notation with the 16 all in the same drop-down box, which is pretty handy. And then we can say, okay, how many subnets are required? Do you want to have 2 or 4 or 8? And what that's doing, that's the equivalent right there of the finger game. Based on 8 subnets, it knows exactly how many additional bits above and beyond this 16 that are going to need to be taken. And if we play our own version of the finger game, we know that is going to be 3 bits that are going to be allocated from host addressing over to the networking side. So our new mask is going to be a /19. It's also calculated how many host bits we're going to have available after the fact, and it played a crazy version of the finger game to determine the actual number of host addresses that would fit based on all those host bits that are available. So as far as host bits go, we have 13 host bits left. And that's because we're going to use 19 for the network, and out of 32, there's 13 left. So if you're going to play the finger game to calculate that many, you go through all of your digits on your hands, then you take off your shoes, start using your toes, or just use a piece of paper to keep track of how many bits. And the process is the same. You keep doubling the number verbally as you bring up an additional bit. So if we play the finger game to 13, we're going to have a total of 8192, but this system knows, as we do, that we have to subtract 2 from every subnet because we can't use, as a valid host address, the subnet address itself, nor can we use the broadcast address for that subnet. So there's the new mask in dotted decimal and in prefix notation with that /19, and all we have to do is click on Submit, and lo and behold, there are our subnets. So we've got the subnets here, the first host, the last host, and the broadcast address, all nicely presented for us, so you can verify your own calculations. Again, that's the IP subnet calculator, available at cisco.com. In this video, we've taken a look at starting our subnetting from an existing subnet, and the practice we do here in this video will help reinforce the other concepts that we've learned in this course so far. What I would ask you to do is, before you continue on to the next video, go back and take a look at the opt-out questions at the very beginning of this video, just to make sure that you can now comfortably and correctly answer those questions. I have had a blast. I'm grateful for the time that we've spent together. I hope this has been informative for you, and I'd like to thank you for viewing. Variable length subnet masking. That's what this video is all about. Here are the opt-out questions for this video. They'll also serve as a great verification at the end of the video when you come back and look at these again to help validate that you understand the information that we've covered together in this video. Let's begin. I'd like you to imagine that our boss has been watching these videos along with us, and he comes up to us and says, I've got a challenge for you. Here's what I'd like you to do. I'd like you to take this network of x.x, really doesn't matter what the first two octets are because they're going to stay constant across the entire subnet, 32.0/23. And what I'd like you to do is I'd like you to carve out subnets for this topology right here. So we might typically say, okay, great, how many subnets do we need? Because that's how many host bits we're going to have to steal. We need 6 subnets. We start writing out 6, plus 2 more is 8, plus 3 more is 11, plus we're going to need a subnet for this connection, this connection, and this connection. That's 3 more, for a total of 14 subnets. So then you and I get out our fingers and play the finger game to determine exactly how many host bits we're going to steal and allocate to networking for creating 14 subnets. And after we do that game, we determine that we need to take 4 host bits and allocate them over to the network address space. No problem. So our mask was 23. Our new mask is going to be 27. That's the 4 additional bits above and beyond what was given to us. So then next, as we start to actually implement this design, we realize there's a huge problem, and that is this. If we use a /27-bit mask everywhere, it is true that we can create enough subnets. However, on each of these subnets, how many hosts can we create on those subnets if we're using a /27-bit mask? And that goes right back to the finger game. Well, how many bits are left over for host addresses? And that'd be 5. We have 5 remaining host bits that are available. And if we play the finger game with 5 bits, that only equals 30 possible hosts on each subnet. And that blows us out of the water right there. We cannot use a /27 everywhere because we won't have enough IP addresses for the host on this subnet. Now, where are we wasting? My mother used to say, and she still does, waste not, want not. Sign, Mom. I love you, Mom. Well, as far as IP addressing goes, we are wasting tons of IP addresses on these subnets. For example, if each subnet supports 30 hosts, how many are needed for this point-to-point connection between router A and router D? And as we look at this topology, you might be thinking, well, Keith, we need 1 IP address on this router interface, 1 here. It looks like we might be wasting, holy shnikers, we're wasting 28 IP addresses on a network that only needs 2. So as our boss is looking at us with a huge smile on his face, we are now going to take a look at how we can solve this problem by using a different length mask in different parts of our network. And it's affectionately referred to as variable length subnet masking. And here's some great news. All of the actual technical skills that you and I need to do this, we have already learned in this course. What we get to do in this video is organize our thoughts and put those techniques we've already learned in the correct order so we can go ahead and pull off this VLSM network design. Our first step in this game, and that's really what it is to identify on our network which subnets are requiring the most valid host IP addresses. And that's step number one right here. Identify the biggest remaining subnets. Now this word remaining, if we haven't done any subnetting yet, that would just be identifying the subnets that have the most requirement for IP addresses. In this case, we have this guy right here. We have 6 subnets that need 50 hosts each. Fantastic. And that's where we start. We really don't need to look at the other subnets or the point-to-point links that require less. We're going to start with our biggest subnet requirements. And then secondly, we are going to create a new mask up to the required amount of host bits available. What we're going to do is we're going to do it a little bit differently than we have in the past. Instead of calculating how many bits do I need to steal from host addressing to create a certain quantity of subnets, we need to ask ourselves the question, how many host bits do I need to leave in place to support up to 50 hosts? So it's still the finger game in the host bits portion, just to make sure we're going to leave enough host bits. So if we play the finger game, to support up to 50 hosts, we need to leave at least 6 host bits available. And then what we're going to do is we're going to have the mask take everything except for those last 6 required host bits. So if an IP address is 32 bits in length, and we're going to leave 6 host bits at the very far right, that means our new mask for this subnet is going to be a /26. So once we've identified the new mask for this subnet, our step number 3 is to simply list the new mask, which we've just done, /26, and calculate the actual subnet ranges. And that goes back to block size. So a /26 has a block size of 64. So I'm going to put right here, router B, and we need 6 subnets. Now the very first subnet is going to look like that parent network of x.x.32.0/ and the new mask of 26. And because our block size is 64, the next subnet is going to be x.x.32.64/26. And the next subnet is going to be 32.128/26. And the next network is going to be 32.192. Again, we're simply adding 64 to each one of these. That's the block size. And now the next network, so we have 1, 2, 3, 4, and we need 2 more to get to our 6 subnets. Now, if we add 64 again to 192, it's going to equal 256, which is higher than any octet can go. And what that represents is we need to go ahead and carry over the 1 into the next octet. Now, we've had an exercise like this previously in this course. This is a reminder of how to do that. So adding 64 more to this is going to go 33.0/26. And the next subnet is 33.64. And I think that completes our 6 subnets. So there are the 6 subnets that we can now use on router B for its local area networks. Now to calculate the actual ranges for each of these, we've already done that also in this course. The very first IP address would be the subnet +1. The last IP address of a subnet would be the next subnet -2. And the broadcast address for a subnet would be the next subnet -1. So now as we continue our steps, when we're done with our biggest subnets, which we are these 6, go ahead and using the very next subnet, repeat those steps. You're kidding me. We're simply going to do the same thing over? And the answer is absolutely yes. So let's calculate what the very next subnet is, and I'm going to put that in blue. So our last subnet that we used was 33.64/26. What is the next subnet? And the block size is 64, so the next subnet would be 33.128. And then we go back and we repeat these steps again. So step number 1 is identify your biggest remaining subnets. And now the remaining makes sense. Okay, got it. If we look at our topology, we need 2 here, 2 here, 2 here as far as host addresses. We need 10 down here. Our next biggest ones are going to be 25 hosts each off of router C. So that's step 1. We're dealing with these 2 subnets of 25 hosts each. And then step 2 says we're going to create a new mask up to the required host bits. So my friends, I'm asking you right now, how many host bits would we need to leave in place to support up to 25 hosts on a given network? Now, if we do the finger game, that's going to be 5 host bits. So we need to leave 5 host bits to meet that requirement. And what would the new mask be if we push the mask all the way up right to the edge of what's required for host bits? One way of calculating that would be to say, well, an IP address is 32 bits long. If we're subtracting those 5 host bits that we need to reserve, the result would be a mask of /27. And that's our new mask. So for this very next subnet, we're going to change the mask to a /27. And we're going to start carving that one out. So this is router C. So that's the first subnet that we're going to allocate for router C. Now it needs 2. So let's go ahead and calculate what the next subnet is. With a mask of 27, our block size is going to be 32. So our next subnet would be .128 plus 32 more, which would make this 33.160/27. And we're done. We've now got 2 subnets that can both support the 25 hosts needed. If we look at this next statement, when done with the biggest subnets, using the next subnet, repeat the steps. So let me go ahead and choose a different color. And let's go ahead and identify the very next subnet to go ahead and use. And with a /27, our block size is 32, so the very next subnet would be 33 dot, and it would be 160 plus 32 more, which is 192. So that's our very next subnet. Let's go back and do the steps again. Step number 1, ID the biggest remaining subnets. Well, we need 2 here on each of these point-to-point links. We need 10 hosts down here. That would make the requirements down off router D our biggest networks that are remaining. And let's also ask ourselves the question, okay, if we needed to have at least 10 hosts on a subnet, how many bits on the very far right, host bits, would we need to leave and not touch in order to create at least 10 valid IP addresses on each of those subnets? And the answer is we would need 4 host bits to pull that off. And so our new mask is going to be a /28. So if we need 4 host bits and the mask is 28, that's a total of 32 bits. It's perfect. So /28 is our new mask. And then step 3 says list the new mask and subnet ranges. All right, so the new mask is going to be a /28. With the /28, our block size is going to be 16. So for router D as in David, our first subnet is 33.192. And because the block size is 16, the next subnet is going to be 33 dot, and it's going to be 192 plus 16 more, which is 208 /28. And the next subnet, we need to go for 3 subnets. So our next subnet would be 33 dot, and it would be 208 plus 16 more, which is going to be 224 /28. And that's the 3 subnets that we need that are hanging off router D for its local area networks. So we've addressed that section of our biggest subnets. Let's go ahead and put a line there, and let's look at the instructions. When done with our biggest subnets, use the next subnet and repeat the steps. Well, the next subnets we have are these 3 point-to-point links that go between router A and B, router A and C, and router A and D. So let's go ahead and calculate what this next subnet would be that's available. It'd be 33 dot, and our block size with that /28 was 16, so it'd be 224 plus 16, which is 240. So that's our next subnet. And the next step is to mask up to the required host bits. So for these point-to-point links, how many bits is it going to take to actually support 2 valid host addresses on a network? And if we do the finger trick for host bits, it's going to equal 2. It's going to take 2 host bits to support 2 valid IP addresses on a traditional network. And so our new mask, if we need 2 host bits here, 2 host bits required, the mask could be all the way up to a /30. And that's what our new mask is going to be. So our first subnet is 33.240 with a /30 mask. Our block size is now a 4, and we can just simply add 4 for the next subnet, 33.244 and 33.248. Again, those are all a /30. And calculating the actual range is the same as it has been the entire course. The subnet +1 is the first valid IP address that we can use right here on router A's interface. And the last valid IP address is the next subnet -2, which we could use, for example, on router D's WAN interface. And what it boils down to, my friend, is the same technical steps that we've done earlier. We're starting our subnetting on non-octet defined boundaries somewhere in the middle of an octet. We're using the block size consistently based on that mask to determine the available subnets. And the other cool thing is there would be no way of meeting the requirement of getting all of this inside of a subnet space using a /23 unless we sliced and diced and used this very cool technique called variable length subnet mask, because the mask here is 26, somewhere else in the network is 27, somewhere else is 28, and somewhere else is 30. And the biggest purpose is so that we're not wasting IP address space in our plan. One other tidbit that I'd like to point out, and it's almost like an afterthought. You can pretend if you want to that you didn't hear it, but I want to make you aware of it because in the real world we often do this. We could use a /31 on a point-to-point link, and instead of considering the addresses being the network and broadcast, because that would be the only two addresses available, on some versions of iOS that is a possibility to do. However, if you are working in the world of CCNA or CCNP, you can pretend that a /31 is a thing of make-believe. And any type of certification or anything else that you're dealing with at those levels, it's going to assume that the longest possible mask for a usable network would be our /30s that we just identified right here. Here's the expert exercise for this video for you. What I'd like you to do is take this same topology. We have 3 point-to-point links. And instead of using these numbers, let's go ahead and create 2 subnets that are 100 each and 4 subnets that are 35 each. And we'll go ahead and do 3 subnets that are 12 hosts each. And what I'd like you to do is calculate an IP subnetting plan where all of that can fit into x.x.0.0/22. And what I'll do, because of the length of the answer, I'll include the actual spreadsheet with the actual subnets in place as part of the Nugget Lab files. So that way when you're done, you can get that from the Nugget Lab files, compare your work to verify that your answers are correct. Our expert exercise in this video is for you to walk through the VLSM exercise that I assigned you. Again, the solutions to that are in the Nugget Lab files. And secondly, I'd like you to go back and take a look at those opt-out questions at the beginning of this video, just to make sure that now you have the ability to answer those questions and confirm your knowledge about VLSM. I have had a great time. I appreciate you joining me. I hope this has been informative for you, and I'd like to thank you for viewing. Testing your IPv4 knowledge. In this video, we're going to step back a little bit from the traditional format I've been using for the videos, and I'd like to ask you 4 specific questions that surround the topic of IPv4 subnetting. And in doing so, it'll give you a chance to reinforce your skills and verify how well you understand the concept and where perhaps you might want to go back and revisit one of the videos in this course. Let's begin. Here is what I'd love for you to do. When a question first comes up, I'd like you to pause the screen. Why? That'll give you an opportunity to read the question and to work through the answer to that question on your own. This will not only give you a chance to rehearse and practice the skills that we've learned together in this course, it'll also give you a chance to validate your knowledge about IPv4 addressing and subnetting. With that being said, let's begin. So here's the first question. How many /27 subnets can be created if starting from the base network of 24.44.64.0/22? And the reason I'm chuckling a little bit is because it really doesn't matter what that number is. What really matters is this mask and this mask. If we're starting at a /22 and we're going to change the mask, steal additional host bits, and we're going to move to a /27, my question is, how many additional bits are we using above and beyond our starting point for custom subnetting? And the answer is we are using 5. 22 plus 5 more is 27. And if we are using 5 bits, think the finger game. If we're using 5 bits for custom subnetting, how many new subnets could we create? So if we play the finger game together, we put our thumb up that has a 2 on it, and we verbally double it every time we bring up another digit. The next digit is 4, the next digit is 8, and the next digit is 16, and the next digit is 32. We have 5 digits up. Our digits representing bits, and the number we said is the total possible number of new subnets. So the answer to this question, moving from a /22 to a /27, gives us 32 new subnets that we can create. A Windows 8 computer on network B, so right there, has the IP address of 172.25.159.227. Congratulations for him. Okay, little Windows guy right there. And the mask is 255.255.254.0, which equates to a prefix notation of 23. The first 23 bits of this IP address is representing the network. Okay, great. So the question really is, what is the broadcast address for network B? You know, my first response is, my gut response when I read this question is, I don't know. Because it's not really easy to see. However, we do have the skills to determine what the actual broadcast address is. And it all starts with that pesky little mask. The least significant bit of that mask in this octet right here, 254, will write out our values: 128, 64, 32, 16, 8, 4, 2, and 1. And this 254 is going 7 bits in, so our dividing line is right there. So our block size is a block size of 2. Now, to figure out what actual subnet this host is actually sitting on, which is our first task really, so we can find out what the broadcast address is, we simply take this third octet of 159 and we'll simply divide it by the block size. So 2 goes into 159, so there's 7 there, that's 14, that's 19, and 2 goes into 19 9 times. So that's 18, we have 1 left over, but we don't care about anything after that decimal point. So now to find the actual subnet, we'll take 2 times, and that result of 79, which equals 158. So the actual subnet is x.x, that's the 172.25, we don't really need to rewrite that out, dot 158.0/23. That's the actual subnet. Now my question is, what is the next subnet? Because that's literally how we're going to find out what the broadcast address is for the previous subnet. So the block size is still 2, and that means the next subnet is going to be x.x.160.0/23. And the broadcast address, which is what they're asking us about. So here's our subnet in question, is the 158 subnet. The broadcast address is going to be the next subnet minus 1. So that broadcast address is going to be x.x for the first 2 octets. And the next subnet is 160, so we're going to back that off by 1. It's going to be 159, and we'll put all 1s on in the last octet. So the answer to this question is the broadcast address for network B, based on this host's IP address, subnet 158, the broadcast address would be 172.25.159.255. Network B is 10.0.16.192/26, okay. Network C is 10.0.18.224/27, alrighty. And network D is 10.0.19.208/28. So it looks like they've got some definite variable length subnet masking going on. Networks X, Y, and Z, that's these point-to-point links here, they're using these networks respectively, all of them with a /30. Fantastic. Okay, so for the question, it says, what route could router A advertise to Corp to summarize these networks? So let's say we're running a routing protocol. We have a VPN connection across the internet. That's how we're getting away with these private IP address spaces. The internet will never actually see the 10 network address space. It'll all be tunneled into global IP addresses as it goes between the Corp router and router A. So back to the question. What route could router A advertise that would summarize all of these networks? So for example, in OSPF, this could be an area border router doing a manual summary, or it could be an EIGRP router doing a manual summary. So how in the world do we figure out what these summary address is going to be? Well, let's find the bits that are in common with all of these addresses. They all start with 10, so the first 8 bits are all the same. And the second octet in all of these is a 0. So that is going to be the same as well. Where they start to get different is that third octet. So let's go ahead and tear apart the third octet. We have 16, 18, 19. That's 16, 18, and 19 right there. And then we've got 19, 19, and 19. Okay, great. So it's definitely the third octet where they start to become different. And all we really need to do is figure out the binary for 16, 18, and 19 to determine how many bits are identical. So we'll put up our chart. 128, 64, 32, 16, 8, 4, 2, and 1. And let's do our calculations here. I'm going to get out my blue pen for this. So for 16, we have 116, and we're done. All the rest are zeros. For 18, we have a 16 plus 2 more, and all the rest are zeros. And for a 19, we're going to have 16, 17, 18, 19. And all the rest are zeros. If you want to practice with binary, there's actually some really cool apps. There's an Android app or two out there that do it. There's an iOS app for like an iPhone. There's also at Cisco's website, they've got a binary game that you can play as well if you want to improve your skills in converting between decimal and binary. So our objective here is to see how many bits are in common. So we have this bit that is in common, this bit, this bit, this bit, this bit, and that one. And then they start to go wacky. So our new mask, when I say wacky, they start to become not common with each other. So for our subnet, we're going to take the value of these common bits which are on, which by the way is just 16. So out of all of these first 6 bits in this octet, there's only a 16-bit on. So the value is going to be 16. That goes right here in that third octet. And then we're going to zero out everything else to the right. And the new mask, we have 8 bits there, 8 bits there, plus 1, 2, 3, 4, 5, 6 bits there. So the new mask is going to be 8 plus 8, which is 16, plus 6 more, which is 22. And that, my friend, is our summary address that Router A could send over to corporate saying, hey, all of these networks, forget about the details. Here's one summary route that covers all of them. Now, the ability to do what we just did together, we walk through step by step in our previous videos in this course of IPv4 subnetting. So if you need a refresher on anything, go back to those earlier videos, brush up, and then come on back. So for this question, the subnets need to support the following number of hosts, including the router's IP address. Network B, they want to be able to put 32 IP hosts, including the router's interface, on that subnet. Network C, they need 62. Network D, they need 300. Wow, holy schnikers, Batman. That is a lot of hosts for a single broadcast domain. However, you know what? That's the requirement. We can still work that out. Normally, we wouldn't want to put 300 devices in the same broadcast domain because that's just a lot of devices. And then networks X, Y, and Z, they just need 2 hosts each for their point-to-point connections. So the question asks us, what VLSM masks? So we're using variable length subnet masking, and I'm presuming we just don't want to waste host address space for VLANs where they aren't needed. So it's asking us what masks should be used on each of the networks, which also could be interpreted subnetworks, because they effectively were talking about the same animal. So on network B, our game that we're going to play is the finger game, but with an eye towards host bits. We want to identify how many host bits are required to be in place to support 32. So we'll play the finger game, starting with a 2 on our thumb, and we'll simply, as we bring up additional digits, we'll verbally double the number. So with our thumbs up, we say 2, another digit 4, another digit 8, another digit 16, another digit 32. And you know what? That might stop some people right there, because they're looking at their hand saying, okay, 5 bits, I just said 32. But because we're talking about host bits, we don't get to use all 32 combinations. We have to sacrifice one for the actual subnet address, and a second one we're sacrificing for the broadcast address for that subnet. So we're really only going to have 30. If we have 5 bits, we're only going to get 30 host addresses out of that, which means we have to go up to 6 host bits to get 32, or at least 32 hosts on that subnet. So out of a 32-bit IP address, if we leave 6 for host bits, that means our new mask is going to be a /26. 32 minus 6 is 26. For the 62 subnet, we just did the math on that. The finger game, if we go up to 6 fingers, we can have exactly 62 hosts. That's perfect. So we can use a /26 there as well. Now for 300, we're just going to keep on raising bits and then doubling the number. So starting with a 2 on our thumbs, let's do it together. We have 2, and then adding that second digit, we have 4, and another one, 8, 16, 32, 64, 128, 256. So with 8 bits up, 8 digits up, that's 256. It's not yet enough. One more takes us to 512, minus the 2, because we can't use the broadcast or subnet address. That gives us 510 possible host IP addresses by using 9 bits for host addressing. So we're going to need, as far as host bits go, we're going to need 9 there. So as far as our mask goes, for the network that's going to support 300 hosts, we are going to use a /23. Because 32, the entire length of an IP address, minus the 9 host bits the mask won't be taking, leaves the mask at a /23. And that's how we could solve this specific problem. Now we're not quite done. We also need to deal with these subnets right here, the point-to-point links. And we could do the finger game for that, or we could just remember that a /30, which leaves 2 host bits, will allow us 2 valid IP addresses on each of those subnets. So a /30 is very appropriate for point-to-point links. So I want to ask you, how did you do on those questions before I did the walkthrough on each one? As you practice with your IP subnetting, your skills are going to get better and better, and they're going to be faster and faster. For many people, I've discovered that going through this course a few times is very, very beneficial, and that's why I strategically put in the opt-out questions at the beginning. So you can start the whole course again, and simply as you take a look at the opt-out questions, decide whether or not you need to revisit that video or not. And if you don't, you can just skip to the next one, and that way you can focus your energies and learning on those areas which these videos will help you on the most. I'd also invite you to go take a look at the CBT Nuggets exam walkthrough for 100-101. That's the CCENT/ICND1. That walkthrough also has a lot of great questions focused on subnetting. And that'd be another way to validate and verify your skills. I have had a great time with you in this course. I am so glad that you joined me for it. I hope that it's been informative for you, and I'd like to thank you for viewing.